we're in Unit 3, differentials. Differentials had lots of different stuff, but first, the purpose. So when we talk about the differential, a lot of times we also mean the final drive. We may say differential and mean the whole entire axle, the rear axle housing, but we're going to clarify some of those things. And first, right off the bat, the differential functions as the final drive. So it's found in axles. But the slang term, if you point to an axle, like a rear axle on a truck or an SUV, a lot of people would call that the differential. So we'll go ahead and go with that. But it's going to do the final gear reduction for the whole drive line. So if you look, this would be the drive, the pinion. The pinion is spun by the drive shaft. And then the driven is going to be the ring gear. So if you were to look at our formula we defined earlier, it's driven divided by drive. If this had 40 teeth and this had 10, it'd be 40 driven divided by 10. That would be a 4-to-1 reduction. It's never quite those easy numbers, but your typical final drive may be 3.23 to 1 or 3.73 to 1 or 4.11 to 1, or if you really want to get a lot of torque for acceleration or for big tires, you could do like a 4.56 to 1. And so that would be actually counting all the ring gear teeth, dividing it by the number of pinion teeth. What you can also do most of the time is look on it and it'll have the ratio stamped. Part of the reason that we want to make it easy for the technician to know that what the ratio is let's say you're working on a 4-wheel drive and you have to rebuild the rear differential. If you put the incorrect ratio in the rear and it's different than the front and they put it in 4-wheel drive, the thing's going to be nuked. Assuming it's a part-time 4-wheel drive. It's a full-time 4-wheel drive, it's going to get nuked whether you put it in 4-wheel drive or not. And so this is the final reduction. Now, in a transaxle, we do have a ring and pinion, but they're typically not this hypoid design, although they used to look like this. These teeth are kind of unique. So we talked a bit about this in the previous unit too, because we looked at like straight cut spur gears, or we looked at helical cut gears kind of with the angle. Well, hypoid is not only angled, if you look, they're curved. They're full on curved. The reason for that, if you paid attention to the assignment, which was the video and discussion, when we bring this pinion in at this angle, we could actually use a little bit more simplified gears, but we needed to drop this pinion down and we needed to get it to engage, not at a 90 degree, like it's coming in sort of more towards the bottom. So there's a lot of this wiping action on these gears. And so they're hypoid mainly because it's not coming in at a 90. And when it does that wiping action, there's some pretty specific requirements for the oil on there. So when you go to service a differential, a lot of times it's calling for a hypoid gear oil. If you look in the fine print on the bottle, it will. It may be GL4, GL5, or 8090, or even 9140 or something, but a lot of times it'll say hypoid because we really have some specific lubrication requirements due to that design. Now, one of the negatives of this design, besides requiring special oil, is this stuff all has to be perfectly aligned. It's not just as simple as getting the teeth to mesh and you're good. We need to monitor exactly where the contact is. So the contact needs to be generally in the center of the teeth. So when we look at the gear set to see if they're in the right position, a lot of times we'll use a marking compound and we'll evaluate exactly where the gear's contacting. You don't have to do that with straight cut gears. You don't have to do that with even bevel gears or most gears. We don't need to really do that. This one is very sensitive, is what I'm going to say, just due to the design. Now, for a bonus, who remembers why we wanted to get this pinion lower for the gear set? Does anybody recall? It was in that video. And answer is, if we brought it right at the middle, right at the center line, that drive shaft would be up higher. You'd have to have a big hump go into the rear seats, or you'd have to run the shaft inside the vehicle and, have little kids get wrapped up in that shaft or something. So we had to drop the shaft down to give a nice flat floor for the passengers on those older, like 1930s and 40s and 50s vehicles, because they were all rear wheel drive. Cool. Okay, jumping into it. Let's do an overview again of that final drive. Let's talk about where the torque comes from. The power comes from the engine, goes to the transmission. Now you know the transmission's going to give us a varying gear ratio, but let's just say whatever gear it's in, is going to turn the drive shaft. The drive shaft, aka propeller shaft, is going to ultimately spline into this pinion. One way or another, they vary. The pinion being in yellow. And the pinion is going to turn the ring gear being in orange right here, but they're in this orientation. So this would be kind of like a side view, and this would be like the top down view. So the pinion turns the ring gear, and the ring gear ultimately drives other differential parts, which turn the wheels. Okay. So that's your overall. And remember, they do have that gear reduction. And then this one kind of shows like front axles. And so this is really more designed to be like what you'd see in a rear wheel drive. Okay. We are going to cover four wheel drive a little tiny bit today, but then unit 4. Yeah, we might be on 5. I don't remember the number. We're going to get pretty heavily into the four wheel drive. And there's a lot of different types, right? But either way, they're going to have differentials. There will be a rear differential. If it's a four wheel drive, there will be a front differential, and those have to be geared the same. They have to be. And then when we get further in, there's even the center diff, and I do cover that just a little bit. So we can have 3 differentials in a, in some of the more high end, like a full time four wheel drive. Cool. Now let's summarize what you did in that discussion. If we were going straight, we would not need a differential. If we're going straight, the left wheel would turn the same speed as the right wheel, and therefore there would be no speed difference, no speed differential. The differential comes from the fact that there's different speeds. Okay, makes sense? Now, unfortunately, sometimes we have to turn. And as you can see in this case, we're turning to the right, which means this is probably not NASCAR because we're not turning left the rest of the day. So look, we're turning right here. If you picture this, sometimes what I'd like to point out is like, let's say you pick an Olympic sport, whether it's track where they're running around the circle track, it's more of an oval, and then or ice skating if it's Winter Olympics, speed skating, or the cycling or all that. Do you want to take the outside path or do you want to take the inside track if you're trying to win?
The inside.
And why would you take the inside? Oh my goodness, be quiet. Why would you take the inside? It's faster, but why does it seem like the people on the inside are going faster?
They're technically going a shorter distance.
Bingo. That's exactly right. So when you go around a turn, this is a longer path and this is a shorter path. And yet they're both poked into the same axle. So if there was no differential, this one would have to speed up and this one would have to slow down, but they can't because there's no differential, right? So you'd end up seeing this inner wheel like you did in the video. That inner wheel would be kind of like burning rubber. It'd be slipping all the time. So that's very harsh, very difficult. So what we'll do, and you saw, I mean, the way that they came up with that differential was just amazing. Build in piece by piece and just, you really got to see how it worked. And that's why for this presentation to really make sense, you need to, this one's not an animation actually. The animation's like amazing and but you can see what they did. There was no animation. They built a piece and videoed it and built another piece and videoed it. It's incredible, I think. So if you've got this base understanding, you know that differential is going to allow this wheel to slow down and this wheel to speed up. And it's not going to break. It's not going to cause anything bad. That's normal. That's a normal condition. So the differential designed for these types of turns. What the differential is not really designed for, though, is to do this forever, right? So they're expecting, yeah, you're going to go around a turn and then you're going to straighten out, and you may go around a left turn and a right turn and straight and whatever. What it's not really designed to do is basically NASCAR. Go around a turn, worse than NASCAR actually. Go around a right turn for the next 10,000 miles. That would not be normal conditions. So the reason I bring that up, if you had a mismatched tire, if your tire in here was larger and your tire out here was smaller, it would simulate a turn, right? Because your inside tire is actually going to turn slower because it has a larger circumference, and your outside tire is going to turn really fast because it has a smaller circumference. That is not a differential, may handle that for a time, but that is not normal. And if damage occurs, don't say I didn't tell you so. Okay. So just an overall of that. Now we'll get way more in detail on this when we add the front differential in, and how come we are so worried about tire sizes when we, or tire conditions when we're doing like all-wheel drive work. Okay. So we'll continue. And as you can see, we just previewed a bit with the four-wheel drive. In a four-wheel drive or all-wheel drive, there's four different speeds. So you got this one, right? This one's going to go slow and this one's going to go fast. But if you look at a all-wheel drive or four-wheel drive, they've actually all got slightly different. The right rear has the slowest, the right front has the second slowest, the left rear has the third slowest. I mean, we'll call this the fastest, second fastest, and the left front has the actual fastest. There's a lot of different speeds going on there in those all-wheel drives and four-wheel drives. All right, so if it's a Tacoma, Jeep Wrangler, F-150, Silverado, these typical trucks, Tundra even, Nissan Titan, if they're trucks that are four-wheel drive, those are part-time, this wouldn't really apply because you should not be on drive pavement on any of those vehicles. Make sense? You should be in two-wheel drive if it's dry pavement. If you need to put it in four-wheel drive, it should be like snowy, muddy, icy, some kind of slippery. And so those tires will slip and not really put so much strain on the drive line. Okay, but if it's a full-time four-wheel drive, we have to have a way to adapt for these different speeds. So the left to right speed difference, we use this differential. The left to right speed difference, we would use, oops, I hit the wrong button. Get it on back here. Okay, wow, this thing freaked out. Okay, the left to right difference up here, we'd use this one. But the problem is, if we have, basically, if you look, the two rear wheels have the shorter path and the two front wheels have the longer path. So the front has to turn faster and the rear has to turn slower. Those drive shafts can't be locked, and that's why we put a center differential. So differentials allow a speed difference axle to axle, but if it's a center diff, it actually allows a speed difference drive shaft to drive shaft. Okay, Mitchell, I saw your hand. Now it's good.
Yeah, I noticed that too because when I on my GX for the center locking differential, there's a lot of warnings all over the vehicle saying not to drive the vehicle while cornering with the center lock engaged because you'll basically destroy the whole drive line.
Exactly. And my specialty is not dealing with the customers. Basically, I would just say don't do that or you break it. But for the technicians, you'd be surprised. This is something that most technicians are not really familiar with because that full-time four-wheel drive is just rare. You guys are with a cool manufacturer, Toyota Lexus. They do all sorts of stuff. So they're one of the few that have the full-time four-wheel drive, like the GX, the Land Cruiser, an FJ Cruiser. If it's a manual transmission, is actually full-time four-wheel drive, but most of them are not. There are some Forerunners that are full-time four-wheel drive. So this concept of the differential, we won't steal the thunder for four-wheel drive because we got that next week, but we will. You do have to understand the differential now so that you can understand it when we apply it to four-wheel drive. So this part's a little bit abnormal, but I think it will help you understand. If you're going to go around a turn, your rear drive shaft is going to turn slower than your front drive shaft. You can just see this in this image. So the standard would be Tacoma, it's in two-wheel drive, so we're chilling. That front drive shaft is not engaged to anything. It's just free spinning. So we're good. We don't hurt anything. But if you were to lock it into four-wheel drive, like if it's your typical pickup truck and it's part-time, it goes too high to four high, boom, and you lock it in four-wheel drive, there is no center differential on those. Okay. So that's why on you can't be driving on drive pavement in four-wheel drive. Makes sense. Now, then we get into the full-time four-wheel drive stuff, and that one actually is engaged all the time, but the center diff is unlocked. So what'll happen is when this drive shaft slows down and this one speeds up, it's using differential gears inside the transfer case. And that's why you can drive on dry pavement. But like Mitchell said, if you lock it, that locks the center diff, you're going to mess some stuff up. Now, if it's an all-wheel drive, you need to log this info because we're going to cover differential types in a bit. If it's an all-wheel drive, that can mean a lot of different things. Okay. All-wheel drive is generally a marketing scheme. So sometimes the vehicles actually work more like a full-time four-wheel drive, but all-wheel drive as a marketing standpoint is for like cars, whereas four-wheel drive is for trucks. So if you get, a smaller SUV and they don't want it to be like, oh, I got a 4x4, they'll call it an all-wheel drive, but the systems can vary drastically. However, your basic all-wheel drive system is all-wheel drive all the time, which means they're going to have to use a technology that's going to either have them constantly engaged, and you see now that's a problem for a different center diff, or more than likely they're going to use something like a viscous coupling, which will basically decouple. It'll be free when you're just driving. And then if you start to slip, it will automatically lock up. And they can do it electronically and they can do it mechanically. The issue with that is it's not a great differential. It's an okay differential, meaning it can do these turns. It can handle these turns. It'll kind of like, it'll let the clutches slip. It's good. But however, if you were to have small tires on the front and big tires on the rear, then your rear would be going slow all the time and your front would be going fast all the time. Those viscous couplings, they don't handle that. That's not what they were made to handle. They're not, anytime there's a big speed difference, it's going to auto try to lock, right? And when it tries to auto lock, it applies the clutches. And when it applies the clutches and you drive 10,000 miles, the clutches are burned out because the clutches have been partially applied the whole time. Makes sense? It's got little wet clutch pack in there. So this is the overview because we have the beautiful arcs right here showing the different wheel paths, the rolling path of the tire. Why, when we deal with all-wheel drive, we're very concerned about tire diameter and really ultimately circumference, because circumference meaning the size of it in a circle, the outside diameter, because that equals RPM. And we can have a little speed difference left to right. Those differentials are made for that. We can have a little speed differential left to right. Those are made for that. Most of them are open diffs anyway. But the center ones, those, they don't really like a whole lot of that. And that's why we're so worried about it on your all-wheel drives. Okay. Cool. So we'll continue. This is just a little cutaway. This is where the center diff is. It's really in the transfer case. It's not part of the drive shaft. Like this picture kind of makes it seem like it is. It's not. So you got transmission going to the transfer case, sending it straight back to the rear diff and also to the front diff. And if it's part-time four-wheel drive, this is just locked up solid. But if it's full-time four-wheel drive, there will be a third differential in there. So that's why you might hear someone say, "Oh, I've got three differentials." Well, yeah, because there's one in the transfer case. Cool. So it's everything about differentials applied to four-wheel drive. The four-wheel drive will come later. Okay, cool. So when we talk about the axles, like we were saying, you could be a 410 to 1, 411 to 1, whatever. And a lot of times these will tell you. It might say GM 10, meaning it's a 10-inch ring gear, 373. So that means it's a 3.73 gear ratio. Okay. Cool. And then we discussed already, if you want fuel economy, you go with like the lower, you go with like some 2 point something, maybe like low threes. If you want a lot of torque and you want big tires and you want race car acceleration, you do the 4.56s, but your fuel economy is going to suffer. All right. That's kind of how this one works. And then if you wanted to do a regear, you can. If it's a rear wheel drive, this is all you need right here. Comes with the ring gear and the pinion. Those, by the way, are married. All right. I've explained this before. When they make the gear, they make the ring gear and the pinion, and then they put them on a machine with some lapping compound and they literally run them together. That's a set right there. You don't change a ring gear and not change a pinion. You don't do that. By the time you change a ring gear and leave the pinion, that pinion has already worn in. It's already, it's almost like two dogs. Like my two, one of them's insane, I know. Colin knows too. But they're a bonded pair. So if anything were to ever happen to us, first off, we'd never let them go unless we died, literally. So, but if for whatever reason something happened to us and they had to go, they're a bonded pair. We don't want to pull them apart. They're bonded. They've got to know each other. They've grown together. That's a pair. We'll make it dogs, so it's not offensive to humans. To yank them apart and put a different gear or a different pet in there, they're going to hurt each other. They're not. You're going to end up replacing that ring gear, and that previous pinion that's worn to the old ring gear is going to imprint its wear onto the new ring gear, and now you basically put a new ring gear in there, and the old ring gear ruined it. That's what I'm telling you. All right, cool. So if you're going to change it, you change it as a set. Additionally, it comes with bearings. I mean, you can see this is not going to be a real expensive set, right? We got like a couple side bearings and a couple pinion bearings. Maybe it comes with a couple different shims because you may be needing to reshim it and adjust it. And a lot of times it'll come with some marking compound and some Loctite. And pretty much that's your regear. Cool. A lot more complicated than that because you have to make sure that ring gear and that pinion are in perfect alignment. The orientation has to be perfect. That's the difficult part about doing differential work. And it requires quite a bit of special service tools. But that's the overall. Right. Now, additionally, we may have ABS type of stuff. So this was just a perfect picture to show this straight thing. This is not another gear. This is a reluctor wheel for the vehicle speed sensor. Okay. The actual teeth are over here on the ring gear. Okay, and then on a front wheel drive, it's going to have a ring and pinion, but like I was saying, they're probably not going to be this curved hypoid gear set. Probably going to be a straight set, and that works. Here's that hypoid requirement, right? It says blah 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 hypoid this and this and this, because again, these teeth they're wiping across each other, so they need some really good lubrication. It has to cling to the gears. It has to really reduce the sliding of the gear across the other gear. Okay. And they did have, like I was saying, spiral bevel gears, but spiral bevel gear would be if this pinion was on the center line, and that's why hypoid's just a bit different. Cool. And then again, we talked about this differential. If this was spinning, you know that this would be going slow and this would be going fast, and this one would be kind of like skipping and slipping and hopping across the ground. So that is summary kind of what we talked about. You guys even notice this is from that video that you did. However, so is this one. So the way that we did that, if you'll recall, our pinion was coming in like this. The pinion is driving the ring gear. The ring gear is turning this arm and all this assembly. This basically, most of the time they'll call this part the center section, but Toyota actually calls this the case. So the ring gear bolts to the case, and all these little pinion gears and side gears also, in a roundabout way, go to the case. The case. Um, the case is not probably my preferred term. The case makes you think it's the housing. The housing is the whole housing. The case is like the part that's spinning, that stuff bolts to it. So we may change over to the center section if you don't mind. Oh, and sometimes they'll confuse it. Some manufacturers will call that the carrier. They'll call that the differential carrier. Toyota doesn't call it the differential carrier because Toyota has a removable differential, and they call that removable part the carrier. Whereas most manufacturers use an entire housing, and then you actually have to put the differential in the housing. You can't pull it out and build it on the bench and put it in. So the terminology, I'm sorry, it's very confusing. It just is. It's the way it is. But I'll get you familiar with all the different types, and then you'll be able to, you'll know. But if somebody says, oh yeah, I'm changing the carrier, you might have to be like, the carrier could mean different things. The case could mean different things. What do you mean? Generally, the housing is the housing, though. That's the good news. So the center section, we'll call it, is going to be the main framework that turns all these parts. The problem, as you can see, these are the axles. If they were splined directly in that center section, there'd be no differential action. So what we do instead, let's say this is actually the right axle, right? Because the front of the car is over here. This is the right axle. The left axle we can't quite see, but if we were to go around, just, well, let's say we're to go straight to start. This would be turning, and this is a 4-to-1. This propeller shaft would turn once. The ring gear would turn a quarter. The axle would turn a quarter. The other axle would turn a quarter. Everything turns a quarter. It all spins as an assembly. By the way, that's what a welded diff does. That's the only thing a welded diff could do. But let's just say you start to go around a turn and it's a right turn. This would have to slow down, and this other axle would have to speed up. So what'll actually happen, this, we'll call this the side gear, but sometimes people say the spider gear, but the spider gear could mean any one of these gears. So that's why I'll specify. This is a differential side gear. This is a differential pinion gear. This is a pinion. You gotta be kidding me. Yeah, I am. This is a differential pinion, though, not a pinion as part of the ring and pinion. Okay, so this side gear will actually start to turn backwards. Believe it or not. It'll turn backwards, maybe like not even nearly a quarter of a revolution. It might turn backwards, let's say a 16th of a revolution on a tight turn. If it turns backwards a 16th of a revolution, it's going to spin this pinion this way, which means the other side of the pinion is differential pinion is going to turn forward, which means it's actually going to help speed this side gear up a 16th. So if this one's going back a 16th and this one's going forward a 16th, it's going to slow the right wheel down and it's going to speed the left wheel up proportionally. Perfect. Exactly. So that's the positive. Now, if you don't believe this actually will turn backwards, I'll help you to understand it. That was a very difficult thing for me to visualize. If this is turning backwards and yet the whole axle is turning forward, how the heck does that work? Well, think about it. This thing is turning. Let's say this thing turned a quarter of a revolution forward. That meant all this turned a quarter revolution forward, but this little gear turned a 16th backwards. Overall, though, it's still going forward. You see that, right? So even if it turned a 16th backwards, if this one turned a quarter forward, It's basically like it's really just going slower. Technically, this gear will walk backwards though, but it's walking backwards slowly while this whole thing is turning forward really fast. That was the hard part that was really hard for me to understand. So if this one was going a quarter, let's just give it RPMs, okay? Just for simple sake. If this thing is going 100 RPMs forward and this one turns backwards 1 RPM, really what I'm saying is this axle's going 99. See how it slowed it down without necessarily making the wheel turn backwards, even though technically that this axle and gear did turn backwards. It's kind of funny. Within the relationship to these other parts. See, so I'm describing all these parts stopped, this would turn backwards, but not if it's going forward at 100 and this one's only going backwards at 1. It's like if you're on a train that's going 100 miles an hour. If you're on a train that's going 100 miles an hour and you walk towards the back of the train at 5 miles an hour, you're going only 95 miles an hour, like that, which is why I had to watch the video. If you don't watch the video, I don't know that this will stick. Okay, but from there, it gets better. If this one went backwards 1 RPM and this one is opposite but proportional, what did this one do? This one went backwards. This one goes forward. So if it was if the whole thing's at 100, this one went backwards 1 mile an hour. That means this one's at 99, and this one went forward. That's like you're on that train and you're walking the same direction as the train. So if the train's going forward and you're walking forward, you're actually going like maybe 105. Okay, so this one would actually go 101. And that's why we're able to get that outside wheel to go faster and the inside wheel to go slower. Okay. Differentials are amazing. There's a problem though. If you guys watched it, you already got it. This design means it'll take the path of least resistance. So if the right side wheel is in the ice and you hit the gas, this is going to be like, oh, the right side wheel is really easy to turn. These spider gears, these differential pinions and side gears, they'll go super fast. And actually, this one will go really fast, just as fast as this whole ring gear and center section. But this left side would do nothing. It'll just sit there, just be chilling. So it's an amazing design with one negative. It's amazing for driving on the road, driving around corners, driving around, good traction places. But if you get stuck and one wheel is in a slippery spot, the other wheel that's on dry ground will do nothing. It'll just be nothing. So what do? We limit the amount of slip. And that's when we get into the limited slip differential, which is mostly, we'll just call like LSD. All right, so if you have some sort of LSD, that would be preferred. Like, especially if you go off-roading and if you have open diffs and you get like one tire in the mud, you'll be stuck. It'd be embarrassing. Or if you're in a cool car, and I wouldn't say you do this, I'm sure you would never do this, but you go to celebrate something, you pull it out into the road in front of the dealership and everybody's watching, they're looking, and you go to do a burnout and just one wheel's like this, and the other wheel's like this. That's embarrassing. That's a good example of why you'd want a limited slip differential. Make sense? So we're going to sell you on the LSD stuff later. LSD could mean multiple things. When I say LSD, it means limited slip differential. Please understand. Okay, so here's the components again. Here's your entire housing. Toyota terminology here. This is your carrier. Okay, and then this doesn't even show all the individual pieces. The next one does. So from there, you can see the drive shaft goes right to this companion flange. Boom, drive shaft to the companion flange. So the drive shaft spins the companion flange. The companion flange is going to be splined to the pinion on the next slide, and I think you'll understand that. Then there's some seals, shims. Sometimes they even have a little oil slinger. And then this differential carrier right here includes all this stuff plus more, and it will all bolt into the housing using all those studs, and there's a gasket right there. And that's something you guys will probably see pretty regularly. This to me this is the nicest type of differential setup, because you can go ahead and you can set all this stuff up on the bench and then load this carrier into the axle. You're not necessarily having to work on the axle like this. You can do it on the bench like this. It's nice. It's a beautiful thing. The other company that was doing that a lot was Ford. Ford would do it like this, and they would have a 9-inch differential, and they called that just the Ford 9-inch. So if you talk with some hot rod guys and like, oh yeah, I got a Ford 9-inch in my Chevy, it's like, why would you put a Ford differential in your Chevy? Because the Ford 9-inch was like this, and it was better. It was nicer to work on, easier to set up on the bench, and then load it up in the housing. Cool. So Toyota does that right off the bat. Now, if you look right here, now we're looking at the case right here. See, I told you Toyota's terminology is a little funky. But a lot of manufacturers would call this like the differential center section. So whatever. Now, this is the main framework. It's got side bearings pressed on, side bearings pressed on. It's got the differential ring gear bolted to it with a bunch of bolts. Then it's got the drive pinion that's actually going to be supported by the, what do you want to call this? The carrier. We'll call it its true names. Okay. That pinion is aligned by the carrier, you see, and then that pinion has to be in perfect alignment with the ring gear. But see, the ring gear is bolted to this case, and so it's all about getting the ring gear and the pinion in perfect alignment. But you may have to move this case within the carrier, and then you might have to move this pinion within the carrier, and there could be shims here, and there could be shims here, there could be adjusters here. There's a lot of different ways to do this, but the visual is this sucker has got to be in perfect alignment with this sucker. Cool. And then additional parts of the case. Within the case, this is the actual differential. So if you look at this, this is more like the final drive gear set. This isn't even really the differential. And this for sure is not the differential. This is more like the rear axle housing. See how I was saying it's slang terms. All right, so once you're in the actual differential, we were talking about how let's say, I think this is still actually the right axle. This is the right axle. The right axle splines into this side gear. The left axle splines into this side gear. So when you see these side gears moving, right, one's walking forward, one's walking backwards, that's controlling your axles. They basically become your axles. But what drives them? Basically, these differential pinion gears, those teeth push on these teeth. If you're going forward, literally the left and the right tooth will push on this side gear and at the same time push on that side gear. And they just turn as an assembly. But if you're turning, they'll be rotating. Cool. So these differential pinion gears really drive the side gear, but what holds the differential pinion, what drives the differential pinion gears is this pinion shaft. So the pinion shaft not only holds them, but it's also what drives them. What drives the pinion shaft, you ask, is the actual case, because the pinion shaft is slid through the case right there. Okay, so there's a lot to visualize. You absolutely will need to have watched that video. Cool. And then sometimes the pin is driven through the pinion shaft, and other times it's a bolt, and we're actually going to show you some of that service. Now, a little, not super critical, but something you should know. There's hunting, non-hunting, there's even partial hunting. A hunting gear set means every tooth on the pinion will touch every tooth on the ring gear. It's an odd number, so they're constantly, new teeth are touching new teeth. Non-hunting means the same teeth touch the same teeth. The reason you need to know this is if you go to do a service on this ring and pinion, a lot of times there could be marks. Well, not really a lot of times, but sometimes in a differential there will be marks. That's because they're not hunting, which means the tooth with the mark on it always touches the other tooth with the mark on it. If you don't line them up, now you have new teeth touching other new teeth. Remember how they're like married pair? They become bonded, right? Like my two sweet girls over there, which are not humans, by the way. I said my little girls once, and somebody thought I had human children, and I don't. But those little sweet girls, they don't want to be have another one put into that pair, right? It's they're done, they're bonded. So if you take a ring and pinion apart and then you put it back together without having marked the gears and they were non-hunting, now you have new teeth touching new teeth, and there's probably going to be whining and gnashing of teeth. There's going to be noise. There's going to be, there's going to be some issues that come with that. Mostly, probably it's going to be noise. There's going to be whining like that. So, is it the standard? Probably no, but sort of the justification here, like you'll see, some of the justification would be, it says timing marks, would be follow service info. Don't just yank it apart. Because if there were no marks, but you were supposed to make a mark, you would have missed your chance to make a mark before you pulled it apart. Okay, that's kind of the point. All right, and then continuing, so talking a lot about differentials. There's a lot of different types, but when we get into the open diff, you'll be able to see there's no limited slip action. It's just straight up. You drive down the road and the diff does its thing. You get one wheel off the side of the road in the ice going up to Big Bear. You ain't going anywhere. You'll see that thing will be that right inner wheel will be, and your left one will be sitting on the drive pavement on the left side of the white line. It'll just be like this, like this, like this. Hmm? Hmm? Nothing. Okay. Then the limited slip we talked about a little bit. Limited slip can mean a lot of things, though. It could be an e-locker. It could be a clutch pack type. It could be a Salisbury. It could be Auburn. It could be Eaton locker. It could be all sorts of stuff. Air lockers from ARB, like a limited slip just limits the amount of slip. It could be the ultimate student welded diff in a 240. Right. That's it. That one would be extremely limited. That would be zero slip ever. Even pulling into the shop, you hear like, so limited slip can mean a lot of things. It doesn't necessarily mean clutch type. Cool. All right. So when we talk a lot about this setup, just know back in the day, we limited slip was like the ticket. Like a lot of cars came with limited slip. And the problem is the older style, like the Positrack, they take extra energy to turn. And back in the 70s, when we had, gas crisis stuff, they're like, hey, we need cars that are good on gas, get rid of those limited slips. And they went to open diffs and they pretty much freaking kept the open diffs. It sucks. The default, if the car doesn't specify, it's got an open diff. A lot of times you have to pay more to get the LSD. You have to pay, like on a Silverado, if or generally on a GM truck or SUV, if you want the limited slip, you got to get that option, and it's called the G80 option, which actually we're going to cover not only in this presentation but as part of the another discussion, right? So you can order it with the LSD. Now, the way that Toyota will do it, if you get the higher option, you get the TRD, the TRD Pro, those will specify what type of diffs they have, what type of LSD diffs they have. Right. If it's a Jeep, you get open diffs. But if you get a Rubicon, you get locking diffs. You can electronically lock them. Back in the day, if you got a 350Z base, you got an open diff. But if you got the one that was like either the track pack or the touring or the Nismo, you got LSDs. So it really varies. I know Subaru does some interesting stuff, but sometimes Subaru's talking more about their adjustable viscous center clutch, center diff. But everybody's got their own way to offer or not offer locking diffs. Make sense? But the default is unfortunately going to be open diff, so you know. Cool. Now we talk about this. This is a really good view. So you see this pinion when that drive shaft turns. Now you can see just how that pinion is going to drive this ring gear. And as it drives this ring gear, the ring gear is bolted to that case center section, and that's going to turn this shaft. This shaft is going to turn these gears, which is going to push on these side gears, both of them at the same time, assuming it's going straight. That's what it's going to try to do. That's what this is showing. And then, right, so if you understand that, and then we're going to add in a turn. So if you're going straight, everything turns. If you're turning left, everything turns at first, but this side, because this is the faster one, will these little spider gears, these little differential pinion gears, you can see it's going to turn counterclockwise right here. That's going to actually speed up this side gear, which is going to make the right wheel go faster. But it's also, because it's turning counterclockwise, it's going to slow down that inner side gear, which is going to slow the axle down, which is going to slow the tire down. So if you're doing 30 around a left turn, your outside tire might be at 31 and your inside might be at 29. But this whole carrier is still turning at 30. It's just spinning this gear backwards and this gear forward to make the 31 and the 29. Right? Then when you turn right, look what happens. The same thing. Differential, the pinion gear turns the ring gear. All that stuff is good. You're at 30. Oh, but look at the difference. Because you're turning right, this differential pinion turns clockwise, which speeds up the left side and slows down the right side. Okay, so depending on which direction you turn, those differential pinion and side gears will start walking. We could, just for simplicity's sake, change that over to spider gears, because if you see how they move, it does look like spiders, kind of like little tarantulas. It's like spider gears are walking. If you're going straight, spider gears are not walking. Why is that critical to you? Well, let's say a vehicle came in and it had a noise from the rear differential, but only while turning. Now you guys can kind of see, if the noise is only while turning, you may be more concerned about these spider gears. But if it makes the noise while you're going straight, you're probably not real concerned about the spider gears. Let's say that one of these spider gears has a tooth broken off. First off, you guys know this tooth being broke off, we'll zing it back here. This tooth being broke off is going to interact with this gear, which is going to mess up that tooth, which is going to mess up this tooth, which is going to mess up this. You damage one gear, it needs all the gears, first off. However, let's just say there's a damaged tooth. If you're going straight, none of these are walking. The spiders don't walk when you're going straight. When you start to turn, this noise comes in. You'd be like, oh, yeah, it could be a broken spider gear, we'll say, whether it's a side gear or differential pinion. Cool. That's why you need to be able to for sure visualize that. Okay, and then we talk a little bit about the housing. So obviously the housing's got to house the differential, but it also needs to be able to hold oil. We need it to hold oil because that differential is going to come down here and dip in the oil, and that's going to lubricate the gear-to-gear faces. Remember, they're hypoid, but it's also going to lubricate the bearings. It's going to lubricate everything, assuming, ready? Assuming it's at the right level. Generally, when we fill it, a lot of times we're making it so it'll just barely drip out of this fill plug, or you can just put your finger in and feel it's right there. A lot of times that means it's going to run down the axle tube, lubricate the axle bearing, lubricate all these gears, lubricate the pinion bearing and whatnot. And an interesting point, I think generally you'll be able to see it right here. If you look, this ring gear is kind of big. These bearings get oiled pretty quick, but this front differential, this front pinion bearing sits up kind of high, because you see how this drive shaft is sloping upward, right? That front bearing, that's up the highest. So if your differential runs low on fluid, that's typically the first bearing to start complaining about it. By the time that bearing starts to make noise, you got to do an overhaul, and that could be thousands of dollars. So it's very important that we check the fluid level periodically, and we're inspecting for leaks and whatnot. This one's nice because it's got the plug on the back. This is a Toyota, actually. This type, sometimes the plug is on the side, but generally there's, well, actually not really true. There's always going to be a fill plug and a check plug. Generally, there's a drain plug, but on this style, there may not be. If this style you had to drain this, you actually have to unbolt this cover right there. And then you have to replace the gasket and reseal it and all that type of stuff just to change the fluid. It is kind of ridiculous. But on a lot of the new ones, they've put plugs on both styles. This always had a plug. Cool. So let's say if you look at this one with the cover, you guys can see the cover's bolted on. If you needed to do differential service on this, you're unbolting this cover and you're standing under the car and you're working on the diff right here. Whereas this one, you could actually pull that whole carrier out and go build it on the bench. That's why this looks welded up right here, because you don't access it from the back. You pull the whole carrier out and go work on it. Cool. That's kind of one of the big differences. And that's what this one's saying. On a removable carrier, you could take it out. It's pretty nice. There's another benefit though. Let's say you're racing. You might want a different gear ratio for a different track. You would actually do a ring and pinion setup in one carrier and then a ring and pinion setup in a different carrier, different final drive gear ratios. You can unbolt the carrier, boom, put in your 456, boom, unbolt that one, put in your 373, right? You don't have to keep going through all the bearing setup and everything. So for racing, that's very preferred. Cool. So continuing, differentials are basically rated by their size and durability. So typically they don't need anything, but if you were to have a car with a whole bunch of power and you were to use like a small diff, you could definitely damage the diff. So this would be like a GM 7.2 and an 8.5. Obviously the 8.5-inch ring gear is going to be much stronger. So sometimes the vehicle will specify the ring gear size. Additionally, the way that you can identify those as bolts. You got a 10 bolt like this. You got a 12 bolt like this. A 14 bolt's gonna be even bigger. So sometimes if you hear somebody talking diffs like a hot rod guy again, they'd be like, "Oh, I got a GM 10 bolt. I got a GM 12 bolt." Basically they're saying if it's a 12 bolt, it's bigger. Technically, okay, this is what I was told incorrectly. You count the number of bolts on the cover. That's not really true. It's actually the number of bolts going through the ring gear into the case. But you can still identify it by the cover. So that's where I think somebody got confused. Somebody looks under there and like they look at this cover and like, oh, you got a 12 bolt, a 10 bolt, and they think it was just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there's 10 bolts. And then this one's a 12 bolt. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Well, that happened to be true. But what we're really going by is the number of bolts into the ring gear. It's basically just sizing the ring gear. It's telling you how big the ring gear is. Cool. That's kind of the GM breakdown. And also you see it's really common by like Dana's. So if you were to look at well, quite a bit of trucks use them. If especially let's say Jeeps, if it's got a Dana 30 or Dana 35 or a Dana 40 or 44, a Dana 60. So like when people go to build, these off-road rigs, a lot of times one of the things they'll specify is like, oh yeah, I got Dana 60s, I got Dana 80s. They'll take these Dana 44s out of their Rubicon and they'll put in like a Dana 60 or a Dana 70, and then they'll do ARB air lockers, and that beefs up the diff. They want to really beef up the diff and make it bigger and stronger because they want to be running their 37s or their 40s or their 44s. If you want to be running 44s, you better go with something pretty hefty like a Dana 80. Right. And then Ford does they just specify by basically by inches, 9.75, 10.25, 10.5, a 7.5, a 8.8. Sometimes Chrysler was doing that too. A lot of the Chrysler stuff, they just Dana makes them. So you just go by the Dana. A lot of times the Dana ones, you could look at the cover, or sometimes if it's always stamped on there, but sometimes it's hard to find it. But if it's pretty clean, you can find the stamp pretty easily, but it's not on the cover. Normally it's on the housing. All right. So there's a lot of info there on differential ID, but so far so good. Now, if it's a bigger truck, they'll actually look at the differential temperature. When you're hauling big weight and working it really hard and stuff, and plus you have a trained driver who has like a Class A license, so they need to know a little bit more than how to push the gas pedal and turn the steering wheel, they'll actually monitor their differential temps. So differentials, when you're working them, they can get hot. That leads into we could have actual covers with cooling fins on them to help keep them cool. Now that's not the fix all, but it does help. It does help. Okay, but also let's discuss. We have a lot of different types: a full float, a semi float, a 3/4 float. Let's define what those are. And we're going to start with the full floating. This was something we talked a little bit about in suspension, but from a different perspective. Okay, so now we're going to talk about differential from the differential perspective. If you've got a heavy truck, you're going to really want this full float. And the reason why, you don't want to put any stress on that axle that's like a radial stress. So if you had, let's say, we'll go with the Tundra. In fact, now we're going to go with the Silverado. Tundras have interesting axles. So the Silverado could have a very basic axle. If you had a light like a 1500 Silverado, you don't need all this. But if you had like a 3500 or a F350 Ford, you would want this. And the reason why, when you put a lot of weight in the bed and you tow a lot of weight and it's pushing down really hard, you got to figure the wheels right here. See, these are the wheel studs. So if the wheel studs are here, the wheel is basically sitting on this whole hub right here, which is this, by the way, right there. Cool. That's what that is. And then do you want all that stress on this axle shaft that goes into the differential? And your answer would be no, not unless you want to bust that off. A non-floating axle will actually literally just have a flange attached to the axle and all the weight's on that flange. If you put so much weight on that, you could shear it off, bend it, that the non-floating, that'd be fine for the 1500 or maybe even a little smaller. But if it's a 3500 and you want to be able to haul, like I borrowed a truck and I hauled 2 pallets of cinder blocks at 90 blocks a piece, I believe. I think it was something around the lines of like 6,000 pounds in the bed, like that. Like it was a big old strong flatbed. That is way too much weight to not be having this full floating axle. The full floating axle, all the weight's on this hub. But if you notice, the hub has a couple different sets of tapered roller bearings and it's transferring all the weight to the housing, not to the axle shaft inside. Now, the reason it's floating, it's from the perspective of the axle. If this vehicle was on the ground and I were to take these bolts out, like, do you see right here how all these 8 bolts are out right here? You could slide the axle out of this one and you could even still have all the weight on the vehicle. The axle is just floating. It literally just drives this hub clockwise or counterclockwise because it's splined into that center section. The axle itself, the axle shaft, holds no weight, supports absolutely nothing. It just makes it go or no go. Makes sense. All the weight is on this hub, and all the hub is on this bearings, and all the bearing support is on the whole big axle tube, the whole housing. Much more stronger. The negative, you need a set preload on these bearings. So if you ever get into something big like this, you don't just get to yank this apart. You got to actually pull the axle out, pull the all the way out, the 8 bolts. There's an axle gasket right there. So now you got to buy axle gasket. And then right here, there's a nut, and that's how you actually adjust this bearing set together. It's almost like wheel bearings we did in brakes. If you tighten it up, it tightens the preload. If you loosen up, it loosens the preload. But you got to set this one up. You don't just bolt it up and ship it. It's different. Cool. So there's your full floating, very heavy duty. ASE doesn't get real into the full float. They might ask a very basic question, not a big deal. And then you got a semi float. And if you look at the semi float, the wheel is on the hub. And then you'll notice the shaft does hold some of the weight. They do have the bearing right here. So that would be pretty light duty. Like that'd be your 1500. Makes sense. But the only reason that this one's maybe just a bit better is at least it has like a bolted in. There's some sort of support here that looks like it's bolted in. Let's jump real quick to this one. Actually, no, this I'm straight now. This axle is literally just sitting on that bearing. All right, so if you put a whole bunch of weight on it, that's going to push all the weight down like this. And this bearing is literally sitting on the axle shaft. That's very hard because the tire is sitting on the hub. And so the tire is holding it, but this axle shaft trying to go down, putting a lot of stress in that axle. See how that's a negative. When you go to pull these out, though, they're pretty easy. There is no setup on that bearing. It just slides into the bearing. That's it. You got to take some brake stuff apart. You got to push the axle inward and then see the C clip. We're pulling the C clip out and then the axle will slide out. But to pull the C clip out, you have to unbolt and pull this pin out. Then the axle will slide in enough to get the C clip out, grab it with a magnet or something, and then slide the axle out. So to work on these, you got to have to pull the cover off. And so this is that like a GM10 bolt. You got to pull the cover to work on this. So if you need to pull an axle shaft, you're draining the fluid, you're pulling the cover, you're pulling the bolt, you're pulling the pin, pushing the axle in, pulling the clip, and then reverse order of installation. That concept will be on the ASE. You need to know this is not a shim. We're not tightening bearing preload or anything. This C clip holds the axle shaft in on the domestic light duty trucks. Cool. And then the 3/4, this is actually what Toyota uses. So I once heard somebody say the Tundra is like a 3/4 ton. And I was sort of like, I don't know about all that. But in a way, I'll hand it to them. If you looked at a 1500, that's got this semi float pretty weak. If you looked at a Tundra, it's got the 3/4. However, the 3/4 floating. But if we break down trucks, a half ton is like a 1500 or F-150. A 3/4 ton's like a 2500 or a F-250. A 1 ton is a 3500 or a F-350, which may or may not be diesel. I would argue with that just a bit because most 2500s are actually going to be full float. So the Tundra is not really like a 2500, but I'll give them this. It's not really like a 1500 either. This is 1500 stuff. This is F-150 stuff. Tundra is a little in between, right? So it's got a 3/4 float. So does the Land Rover, by the way. So like these axles are a little beefier. I'm not so sure that the suspension is going to be able to, compare like with strength to a 3/4 ton, but the axle is getting closer. All right, so pretty good design on those Toyotas. To do these, you actually have to unbolt this bearing. So it has like a bearing retainer and you slide out. You don't have to go inside the diff and pull any C clips. There's no C clips. You undo the brakes, you undo these nuts, and you actually slide the whole shaft out. I'm going to show you some pictures of that coming up. All right. Then when we're doing this type of work, there's two things you got to measure. If you put a dial indicator on the axle and you spin it, what are you measuring? Who thinks they know? You better know this. You can answer it. Or I'll answer it for you. So that if you're spinning it like this with the dial indicator, that would be run out. That would be like axle flange run out, just like a rotor. However, if you're taking this axle and you're moving it in and out like this, that would actually be end play. So it could be run out or end play, depending on which way you're moving it. ASE has questions like that. You got to look at not only the dial indicator, you got to see, are they saying it's getting turned? That'd be run out. Are they saying it's going in and out? That would be end play. Cool. And then part of the reason we do that inspection, if we have a leaking axle seal, like you see, this thing is gooped. This thing is leaking differential oil. That diff is going to be low. The next step is you're going to burn up bearings type of thing. But if it's leaking like this, yeah, you may need to replace the seal, but you also may have a bearing that has like, it's loose. That axle may be moving. That axle may have excessive end play, so we need to do some of those measurements to see, is something causing the seal to leak or is the seal the cause of the seal leaking? Okay, it could vary. Nasty though. Plus it's all over the brakes. Now you know the true purpose of the splash shield. It's to try to keep oil and contaminants off of your brakes so you can still stop and whatnot. It's kind of important. Then once in a while you get an axle shaft that's got a groove worn in it. And you guys already know if you got a groove worn in a shaft, the seal's not going to really be able to seal. So they might actually sell a little sleeve that you can slide on to give it like a new surface. But really, that's kind of a janky repair. I would go ahead and replace the axle if it's got a groove. Cool. All right, so looking for fluid leak, as you can see, it looks horrible. Some of this is going to be the steps of how to do it. Okay, so we're going to do quite a few of the processes to get you an idea of how you do the service, but then we still got to come back to how to set up the diff, and then we still got to go into limited slip differentials and still the concerns that people typically have relating to a diff, noise, vibration, these things. Okay, so if you're looking for fluid leakage, clean, go ahead and look at it, but you may need to really clean it to try to find out the root source, the original source. That would be an axle seal, by the way. Generally, this is actually a pinion, so you'll notice this is out at the backing plate. This is at the drive shaft. Two different seals, two very different jobs. The pinion seals actually can be kind of technical to do. Okay. And then why would you suspect we're really worried about checking the vent or the breather? You're going to notice this is similar to like automatic transmissions. What would a clogged vent or breather cause? The answer would be the fluid gets hot, it tries to expand. It can't expand because the vent is clogged. It builds up pressure and pushes seals out and makes it more prone to leaking. So if you have like one seal leak, it's probably not a big deal. But if you have, two axle seals and one pinion seal leak, and you're like, why is this thing, all this stuff leaking? Check that vent for sure. That would be an ASE concept too. Cool. And then looking at this rear cover, or in this case, this is the carrier bolted into the housing, looking at that gasket for leaks. There was a recall a while back, a campaign for retorquing those bolts on Tacomas. I don't know if you guys got to do any of that. Checking the fluid level, especially if you see a leak and they don't want to fix it, if you at least top it off, you can probably help save the diff. Cool. And then if we're going to do a domestic style, removing a domestic style integral axle. These are the steps. You see, we're pulling the brakes right here, dealing with the parking brake, pulled the cover. The next step, we're gonna, yeah, we removed the differential cover. I thought we got that. Clean the cover, got to get it ready. Then we need to take this bolt out. This is that differential pinion shaft. So we'd have to take the bolt out, and then this pin will slide out, slide that pin out. Then at that point, there's enough room to shove the axle in, and see, now it exposes the groove. When you slide this in, it traps the C-clip in this groove, kind of goes in the side gear, and then the pinion shaft holds it back there, and the axle can't come center to have the clip fall out. Makes sense? So that's the order, right? Pull the bolt, pull the shaft, push the axle in, pull the C clip. Then you can slide the whole axle out. And this would be that semi-float or really non-floating axle where the weight is on the axle shaft. That's why it has this bearing riding right on it. And by the way, there's not even a race right here. It's the bearing riding on the shaft. So if the shaft gets damaged, it needs to be dealt with. It needs to be fixed. Whereas, like, if you're doing that floating axle, that hub has the inner and outer race that has its own races. That's much more serviceable. This is fine as long as nothing goes bad, but when it does go bad, it's a little rough. Cool. So we can slide it out. Now you can see you can get at this axle seal. That's how you do the seal. And behind the seal, there's a bearing. So you see the little bit of this roller right here. So if you had to do axle bearings, you got to pull the seal first, then you got to put a slide hammer in and pull the axle bearing. And the axle bearings would have all the same symptoms as a wheel bearing. So if it's the right side axle bearing and you go around a left turn, that right side axle bearing gets more weight on it, and that would make the noise. Assuming it's one of these semi-float or non-floating. If it's a full-blown floating axle, it wouldn't really be an axle bearing. It would be those actual big hub bearings out there. So it's not a wheel bearing in a rear wheel drive with a solid axle. If it's got an independent rear differential, it could actually have its own wheel bearing because the diff is just the diff, and then a CV axle comes out, and then it has a wheel bearing. Okay, but if it's a solid, a live axle, if you will, there is no wheel bearing, it's an axle bearing, but the symptoms are the same. But the replacement's way different. Okay, and then we get that new bearing in there, set that thing with a driver, get the axles in, put the C-clips in, put the pin in, put the bolt in. I had somebody once leave this bolt loose. That bolt needs a little Loctite right there, let me tell you. That bolt backed out, the pin fell out, the circlip fell out, and the axle walked its way out, and they had the whole wheel and caliper and all walked way out. Or it was a drum. It was the wheel with the drum on it. Like it was sticking out from the car like 2 feet. It was pretty hilarious looking. And then getting it prepped, gasket, sealant, reinstall the brakes, bleed the brakes. That's the type of work. And then, of course, fill the fluid. You see, this one has the fill plug on the side. That one's kind of fun. A lot of Toyotas have it on the back. And then, of course, road test, make sure you don't have any noise, make sure you don't have any leaks anymore, and etc. Okay, but what if it's a carrier style, like a Toyota style? Pull the wheels, pull the brakes, and then look at this. This is different. We're out here at the axle, and we're unbolting a bearing right here. It didn't say anything about pulling the cover off to slide an axle out. To slide the axle out with this, you got to actually unbolt this bearing plate. Cool. Then you can slide it out. See, so this has the actual bearing plate on it. All this is going to stay together. The bolts went right through this housing. And yeah, that's why big part of doing differential work can tend to be brake work too. Cool. Slide that out. You can still replace the seal right there. But you'll notice there's no bearing behind the seal. The bearing is the bolt-in part. In that way, that's why these are a little more heavy duty. The bearing's really sitting, it's bolted to the flange. Cool. And then you can see that's got the new seal in. We're reinstalling the axle. And then right here, we're bolting that bearing plate back up on this 3/4 float style. It's kind of floating, but not totally. All right, then putting all the brakes back together. Checking the fluid. Now, this is a cut from a different one. If you wanted to replace that bearing, you need something like this. You need the press, and it needs to be able to go into an adapter. The press needs to have a lot of space. So replacing those axle bearings on that 3/4 float, like out of the Tacoma or Tundra, well, really any Toyota full SUV with a solid live rear axle, you need some pretty special tooling to be able to do that axle bearing. You don't just get to pull it out with a little slide hammer and like tap it in with the driver. You got to put that thing on the press. So this is one of the tools used. This is the easy semi-float or non-floating. You see the slide hammer hooks the edge of the race and you just pop it out. Much, much easier on the domestic style. Cool. And then of course, if we're going to do that type of work, replace the seals. So this would be an axle seal. We're going to get to the pinion seal as well. And then remember, inspect this axle shaft. If there's a damage right here, you really need to replace it, or you can consider that speedy sleeve thing we talked about, but it's not really recommended, as a good fix. It's like oh, you don't have the money? Let me try to do a miracle for you and fix it with this other little janky thing. Cool. So then when we go to be pulling the axles and stuff, a lot of times it'll pull, let's say that we were going to do a, uh, like a remove the carrier or do the seal. You're seeing a lot of this stuff is kind of similar. So once you get the hang of servicing these differentials, it's not a real big deal. But if we're doing this bearing, there's that pressing the bearing off because it's got the splitter. This is the bearing right here. Okay, and then we go to reinstall it. There's the new bearing right there, getting pressed in the housing. We go to reinstall it. This is another adapter, and it actually bolts to the flange, and then you're pressing the bearing on this big adapter. So that's what I'm saying. You need a couple different tools. You might be able to remove it with some common stuff, but when you go to press it, you need this tool because it's a seal driver. It's a bearing driver, but it's long because it's got to actually go over the whole housing and press it down at the base. So it's a beast of a tool. All right. Anybody seen that in the shops? It's not super common, but it does happen. If you're the DIY home mechanic, you know what you're going to do? You're going to buy an axle from a junkyard with the bearing already pressed on it. You know, put that whole thing in there. And it doesn't matter the gear ratio. It just has to be the same type of differential housing. Because this slides right into that side gear. Boom, good to go. Cool. And then let's say it's a pinion seal. This is a bit different, and I'm gonna add some very critical details. If this pinion seal's leaking, like this one is, right? And you guys may see that on the trucks and SUVs. It's a couple ways to deal with this. One, you say, oh, it needs the whole entire rear axle carrier, which is kind of nuts. Or two, if you do want to fix it, I'm gonna explain to you how you can and also how you're supposed to, because they're different. Right, so you see the leak, right? You'd have to pull this companion flange or pull the drive shaft out. Then you're going to see behind this drive shaft, you know, it's the flange or the yoke or whatever, there's going to be a nut right there. And then this is the thing you have to understand. If you remove the nut, you've now changed the pinion bearing preload. Okay, so I'm editing what this says. This is the gist of it, but I worked with a guy, so I'm gonna tell you it's a true story. I was thinking about saying the name, but I probably won't. And he was like 1 year ahead of me. In fact, I think he was a general auto guy, not he wasn't manufacturer, but I'm not totally sure. But whatever, he was 1 year ahead of me, and like you, and hopefully many after you, he did his time, did the lube tech work, did the schooling, handled some stuff, passed some tests, got his credit, but they're starting to like let him do a little bit more, right? That could be while you're in school, that could be right at the end of school, that could be like slightly after school, but he started to get his work. And I remember he recommended a leaking pinion seal. And so he worked a little bit with like a mentor, but not that much. And that's kind of why this is a problem. But he recommended this pinion seal because pinion seals can pay okay. It's an hour or two, and you can knock them out. So he recommended it. When he went to do it, he just yanked the nut, blasted it off, pulled the little yoke, pulled the seal, drove the new seal in, put the yoke back on, and then he was like, you just tighten it like you just send it. So he tightened it up. You got to understand when you tighten that up, you're squeezing the bearings. You're setting the preload right there. So he blasted it super tight and then he went to turn the differential and it was locked up. So what would you do if it was locked up after you over tightened it? He knew he over tightened it. What would you do?
Isn't it?
Exactly what he did. Now, this is the scary part. When you over tighten it, you're crushing this part called the crush sleeve. It's coming up. Then when you loosen it, now that crush sleeve is very loose and those bearings are actually sloppy. So what's going to happen is that whole pinion is going to be moving and rocking around, right? So don't over tighten it because if you do, you can't just loosen it. But he was kind of like, oh, whatever, I'm gonna send it. So he loosened it and sent it. It came back like a week later, and the whole pinion had been slopping around like this, messed up the end of the teeth, messed up the teeth in the ring gear, ended up nuking the pinion bearings. That diff basically blew up. And it blew up because he over torqued it and then he under torqued it. Okay. So, and it all started with a pinion seal. So they were kind of like, hey, did you not know? Did you not have any idea? And he's sort of like, I don't know. And just like you just loosen it and you just put the seal and you just tighten it. It's not that simple. If you were to look on TIS or service info to replace that seal, it's actually going to tell you to disassemble the differential and put a new crush sleeve in there and then reassemble the differential with the new seal. You're basically doing a diff rebuild to replace that seal. Okay, so you got this guy's name was Richard. Okay, you got the Richard way, which was like you don't really know, yank it out, pound the new seal in, tighten it up, under tighten it, over tighten it, etc. or you've got the TIS service info way, which is like basically you're redoing the whole diff. You get to go ahead and you get to rebuild this whole diff. So I'm gonna try to give you the in between. Understanding that that big nut right there controls your bearing preload. What you're gonna do is you're gonna scribe it, scratch it, make a mark where that nut is to where the pinion is. Then you're gonna take it out, do the seal. You're gonna do just like what Richard did. But you're gonna put it in, and then when you go to torque it, you're gonna turn it to where that line is, and then go the tiniest sliver more. And all that's going to do is slightly crush that crush sleeve, just a tiny, tiny bit. And if it slightly crushes the crush sleeve just a tiny bit, it's still going to be in spec, but it's not going to be over torqued to where it's damaged to where it's going to end up loose. Okay, so that's the flat rate way to do that job. Kind of make sense? A little bit? Yes, 1 second. All right, so not super complicated, but that's how you do the pinion seal the flat rate technician way without messing it up. Okay. So if you ever need to do one, you could always let me know. But there's probably also quite a few videos on how people are doing it successfully. Just don't underestimate if you over torque that, you can mess it up. Cool. So here we go. And then you can see there's your new seal, and that's kind of what this is saying. According to service information, you can't do this, but in reality, you can torque this nut to spec, but you just have to understand that doesn't account for over crushing the crush sleeve. So I wouldn't do it like that. I would make the mark and do the mark. Okay. But when you do tighten this up, it has to at least meet the minimum torque spec, but a lot of times you'll meet the minimum torque spec, and then to set the preload, we're actually over torquing because it's crushing. It's kind of a weird thing. When you see the steps for doing a diff, it'll make sense. Then of course at the end, make sure that we don't have excessive run out. If you were to have excessive run out on the flange, that's going to cause a vibration and end up causing damage to the diff too. Customer's main complaint would be vibration though. Figure if that flange has run out, it's going to go like this. The drive shaft is going to go like that. The whole car is going to shake. All right, so speaking of issues, typically, one of the main things that we deal with would be noise and vibration. So noises, that could be something like bearings. That could be something like worn teeth, like say ring and pinion teeth, differential pinion and side gear teeth. Generally, if it's bearing noise, it probably is going to have been caused by low fluid level. So if the fluid level's low, we could get the fluid level back up to full, but by then probably the damage is done, kind of like an engine. If the oil is low and it starts knocking, by all means put oil in it, but don't be surprised if the knocking doesn't go away. The damage is probably done. Similarly, but once the bearings are damaged, then we really need to fix the bearings. However, if you fix the bearings and you don't address the leaks, you're probably going to end up with repeat failures, right? So it's kind of interesting. We do the MPI. If you do the MPI well and you actually check the fluid and you top it off if it's low, you probably won't. The customer shouldn't really have any of these bearing failures. So we're self-justifying by preventative maintenance. Our preventative maintenance service, like the oil change MPI, even if it's $100, that's cheap if we're preventing a lot of these issues. Makes sense? So preventative maintenance by design should save the customer money. Yes, we're taking their money, but we're saving them money by not allowing the vehicle to get to the point where it's breaking due to something that's preventable. Is the vehicle going to break? Probably still going to break, yes. But if it's preventable, I'd like to see the preventative maintenance prevent the failure. The maintenance is going to be cheaper than the repair. Okay. Then a lot of the other things we're dealing with, right? So noises, probably bearings and gears. But vibrations, typically a little bit different. A vibration a lot of times would more have to do with maybe the drive shaft balance or maybe an axle balance. But and it could also do with some of the things we talked about with changing the driveline angle and universal joints and stuff. So typically noises and vibrations are what we deal with, but a lot of times the vibrations wouldn't normally be the diff. It could be, but it wouldn't normally be the diff. Now let's just say one example of a noise was you're driving, customers driving ASE style, and when accelerating, it's quiet, but when you decel, it's noisy. And Tech A says it could be, let's say, pinion bearings. And Tech B says it could be ring and pinion gear wear. I would go with Tech B only. Pinion bearings, they make sounds, but like when you're pushing the gas pedal or not pushing the gas pedal, it might change in pitch, but it won't totally take it away when you push the gas pedal if it's a bearing. However, if it's the ring and pinion, when you're driving, it's these sides of the teeth, but when you're decelling, it's this side of the tooth, right? Drive and decel. Drive and decel. They'll call it coast too. Right. So if you have damage on the coast side of the tooth, it would only make noise when you're slowing down, but it would make no noise when you're speeding up. Right. So a lot of this is the differential type of stuff that could be noise related with ASE and with cars in the shop too. Okay, but we're going to continue. So this, for example, is a spider gear defect. If this is a defect on the spider gear, when would you hear it? Anybody care to give a shot?
Unturns.
Exactly. Bingo. So if ASE words it in a way where it's like going straight, it doesn't, but turning it does, you might be thinking damage on the spider gears, on the side gears or differential pinion gears. Cool. And when we jump into limited slip stuff, there's a lot of other additional parts. So if we've got clutches and extra shafts, and sometimes they have little flyweights, and sometimes they have cone clutches, and they can have all sorts of stuff. Those can be even a little more complicated, I'd say. Like for example, I remember it specifically on this big van. We used to call it the G van because it was in the VIN. It was the G model. It was like a Chevy Express. It was a big, it's a big hollowed out van. So that thing is like an echo chamber in the back. And when you would, and it also had a locking differential, but the way that the G80 Eaton locking differential worked was it didn't like slowly apply the clutches. You had to slip the wheel enough and then bam, it would be engaged. And it was pretty, you could feel it. It would only do that when, like, after a snowstorm, you'd have spots of snow and dry pavement and snow and dry pavement. So if you were just cruising and you were on the dry pavement, everything was good. But then when you hit the snow, the rear wheels might start to turn. And if the one rear wheel turned faster and the other wheel turned slower, it would engage that G80 and it would like bang and shudder and then you'd like there was noise, there was vibration, there was harshness, and it was all normal. It was entirely normal because the differential was locking up when you went across those snow drifts. So the locking diff stuff adds another layer, if you will. Cool. So we talked quite a bit about those. Now when we're jumping into the bearings and stuff, we talked some about those full floats and whatnot. They have axial and radial. Radial would be the weight on them. Axial would be when you turn, it tries to slide in and out like this. So they can, have some failures. One of the main reasons would be low fluid level. One of the main reasons the fluid level is low would be due to a leak. But then by the time it starts to make noise, like I said, it's mostly probably too late. And a lot of times they'll cause a growling noise. So if you hear the term growling, we're most likely talking bearing. You could say whirring, but I would more go with growling. Bearing growl is what they do. But they might change in pitch. If it's pinion bearings, it might sound a bit different. It might be a little more high pitched because the pinion bearings travel faster than let's say, the differential bearings or the axle bearings, right? If it's a 4-to-1 ratio, the pinion is turning 4 times for every axle to turn once. So your pinion bearings may be more like a woo, and your axle bearings may be more like a woo, because they're different frequencies due to different speed. Cool. And we have different ways to kind of narrow this down. So if we think it's those axle bearings out at the ends, how would we manipulate that noise? We think it's one or both of the end axle bearings. Steering the vehicle is going to change the load on that bearing because the weight's going to shift to the outside. And if you turn left and it gets louder, I'd say it's probably that right rear axle bearing. It's coming from the back. But if it's a woo and you can change the pitch, just like tipping your gas pedal a little bit, accelerator, like woo, then I'd more be like, hey, that sounds like a pinion bearing. When you're loading and loading the pinion more or less, that's going to change the pinion bearing because you're putting more load on it or less load on it, right? That would be kind of some bearing diagnosis. If it's a noise that's steady, it doesn't change with any of that, but it increases with vehicle speed or decreases with lower vehicle speed, then I'd more think those side bearings, right? Those are the ones that are right on the differential case or on the center section, we'd call it. Those, you can't really change the force on those, but you can change their speed, right? So it's a pretty good method to just understanding how you're varying the force in these different bearings. But the other thing is you could do a stethoscope or a chassis ear and put it in the different locations while you drive it, right? So there's multiple ways to really narrow it down. Cool. So now when we talk about overhaul, let's discuss. It's all about setup. Okay, so there's 3 things we're worried about here. There's backlash. Backlash. You set the backlash. Not to be confused with a backrash. This is the lash, not the rash. Okay, so this would be an example of backlash. If I were to put a dial indicator on my thumb and then move it, I could measure how much clearance there is between the gears. So backlash is just a way to measure the clearance between the gears. Okay. Then there's the tooth pattern. That is the last step, and that really tells it the whole story. Then there's also the bearing preload, and that just basically is like, how tight are the bearings? If the bearings are loose, it spins easy. If the bearings are tight, it's a little harder. If they're too tight, they don't have lubrication in the rollers and they burn up. If they're too loose, they're sloppy and they self-destruct, and also, they don't hold things where they're supposed to hold it because it's too much play, right? So if we set good bearing preload, good backlash, and we verify it with the good gear tooth pattern, chilling, big chilling, be beautiful. Because remember, these hypoid gears, these are very sensitive to their locations. Now, to do this read, you have to know some stuff. All right, so let's say you're all going to have to look down at your feet. Hopefully got some kind of shoes on. But if you look at this gear and you were to walk up to it, your heel is like at the back, right? So this is the heel side. The outside is the heel. The inside is the toe. Okay. First off, look down. Same thing. You set that ring gear in front of you, and then you look down at your feet, and the heel is towards the heel and the toe is towards the toe. Cool? Everybody should be good. From there, we're actually going to jump over here to the root, which is like the base of the tooth down here, and the top, or sometimes called the crown, right there. Root and crown. So root, if the tooth's like this, root would be way down there. Crown would be way up here. Okay. And then the drive and the coast side. So when you're driving, the ring gear is being pushed by the pinion on this side. So we a lot of times will call this the convex side. Okay. But when you're decelling, basically what's really happening is the coast side, which is the concave side, is actually going to be pushing the pinion. It's kind of interesting when you're accelerating, the pinion is pushing the ring gear, but when you're decelling, your ring gear is actually pushing your pinion. That's why you get some engine braking, right? That's why basically we talked quite a bit about like regenerative braking and stuff. It's because literally your axles, your wheels, your whole vehicle pushing your axles, pushing your wheels, pushing your axles, it's actually going to push your ring gear into your pinion using the coast side on the convex side. And that's literally going to power this pinion. And we could send that pinion into an MG2 and have it become generator number 2 and generate electricity. We can also control how much magnetic field opposes that. The more we oppose that with a magnetic field, the more it'll put resistance on it. It'll give us more regenerative braking, but also make a more power. So this kind of overlaps a bit with engine braking, with regenerative braking. Okay. Engine braking works similar, except you're not harnessing any of that energy. What you're doing is basically it'll do fuel cut. If you're on full decel, it'll cut fuel and it'll basically spend that energy that's pushing you downhill, which is your momentum of your vehicle, and it'll just make that pump the pistons, and it's pumping losses at that point. That's how it slows you down. Cool. So there's your whole, and if it's, you take it a step further, if you got an engine brake, a Jake brake, that's actually going to further put resistance on your ring gear, which is going to, on your pinion, which is going to slow your ring gear, which is going to slow the vehicle. But it all goes through the drive side or the coast side. Now, if you had a big defect on the drive side of these teeth, that's why you'd hear it accelerating, but it would go away on decel. Or the other way, if you had a big defect on the coast side, you'd only hear it on decel. You wouldn't hear it on drive, right? So they're two different things. Okay. And then when we talk about a backlash, the backlash right here, that's the clearance of the gears. So if you look at this one, this backlash is a lot, but you can't fit your feeler gauge down in there. This backlash is tight. You also can't fit your feeler gauge in there. So what we'll do, we'll put a dial indicator on this, and as you move it, you can move it, let's say 30 thousandths, it'll move your dial indicator 30 thousandths. You know there's 30 thousandths of clearance. That'd be too much, by the way. So how do you make it less? Well, either A, you make the tooth fatter, and you can't. So instead, what you do, if you look, you bring it down. So here you go. You ready? You can do this. You could do this at home. Voila. Voila. This is kind of loose right here. Too much backlash. You want to tighten it up? Oh, too tight. Right in the middle. Right in the middle. Makes sense? So it's all about this. How do we do that? Well, we don't move the pinion. Generally, once we set the pinion, we want the pinion to stay the same. What we do is we'll move the ring gear. You move the ring gear. If the pinion's right here and you move the ring gear closer, that's tighter, looser, tighter, looser. Okay? Not that big of a thing. You can do that. But that's why we measure the backlash, and we will fine tune the backlash. Okay. So like you can see, this is a good image of that. If the backlash is too tight, you'll move this ring gear to the left. If the backlash is too loose, you move the ring gear to the right. How? Ooh, now you're running into some of the problems. Okay. Ideally, it's got adjusters. If you wanted to move it away, you'd loosen this adjuster and you tighten this adjuster the same amount. But if it doesn't have adjusters, and a lot of the domestics don't, sorry, then you'd actually have to do shims. So I'm gonna tell you something to help you understand it, and it's not accurate, and then I'm gonna fix it. If you wanted to move it away, you would take shims out on the left and you would add shims to the right. Can you see how that would move it away? Cool. Take shims out, add shims. If it was too much backlash and you want it tighter, take shims out from the right and add them to the left. Let's just say each shim was 1,000th of an inch. If you thought you had to move it 10, you'd pull 10 shims out from the right and put 10 shims to the left. Okay, but now I'm going to fix it. There is only one shim. You don't have multiple shims. So if you want to take shims out from the right and put them to the left, well, what you really need to do is get a thinner shim here, 10,000ths thinner shim here, and a 10,000ths thicker shim there, which means you got to be measuring with your micrometer. Okay. Why would we move it? Because the backlash is messed up. If the backlash is not in spec, that's when we have to get into measuring these shims and doing the calculation and moving it. But now I'm going to add another complication. Dang it. Pinion depth. Ugh. And then we'll discuss each of these in order. Okay, because this is just giving you the concepts. This is not really in order. The pinion depth all has to do with how deep this pinion plunges. So if this is the outside of the differential case or the carrier, the pinion is going to go either deeper into the ring gear, because the ring gear lives down here, right? It's going to go either deeper in the ring gear or shallower in the ring gear. If we were to look at that, that would be controlled by this shim right here in yellow. Right? So if the pinion depth is too shallow and we need it to be deeper, we use the thicker shim. If the pinion depth is too shallow, it is is too deep and it needs to be shallower, we'd use a thinner shim. So I'm gonna try to help you visualize this. The ring gear's down here. If it's shallow, that means it's not plunging deep enough. If it's too shallow, how do we make it plunge deeper? We'd add to this yellow, right? And that would make it poke deeper in there. Or if it's too deep, like it's running off the edge of the gear, then we'd have to back it up. And how we back it up, we'd have to pull shims out, right? This pinion, head of this pinion is always pressed right up against that shim. That shim either sets it deeper or lets it go more shallow. That's the purpose of that shim right there. That's all that shim does. Kind of make sense? Sort of. So there's all these things going on. Now, the thing is, though, if you change your pinion depth like this, remember how I was saying, if we have the ring and pinion like this, we're talking mostly about moving the ring gear. But if I change the pinion depth, that could make it tighter or that can make it looser. So in reality, we actually set the pinion depth first, because the pinion depth is very, very difficult to adjust. If you want to change the shim, you got to pull the flange. You're going to drive this pinion out with a press or an air hammer, and that's going to probably ruin this bearing. Then this bearing's still going to probably be okay, but by the time you need to get this shim, you need to pull this bearing off, at which point you're going to ruin this bearing all to get to that shim. So you basically kill a pair of bearings to do the shim, and those bearings aren't cheap. So you do it first. If you're just doing a re-gear, you're probably just going to reuse your old shim, and it's probably going to be correct, because the main reason we have this shim is to make up for machining differences, and it mostly has to do with the housing. Maybe a little bit with the pinion, but they get the pinions pretty consistent. The housing of the differential can really vary. Or in this case of a Toyota, the carrier can really vary. So if you're pulling your old pinion out, you could probably reuse your old pinion shim, unless you're doing a whole new housing and a whole new pinion, in which case you're screwed. You're starting from scratch. That's a mess. That's a mess because depending on who you listen to, you're going to have to basically set it all up and do the gear pattern check. And if your pinion is showing too deep, you got to pull it all back apart. You just bought another set of bearings. So I'll give you a couple of options here. One, you take your old bearings, and your old bearings right here are pressed onto the pinion, and you use a file or a Dremel or a die grinder, and you open those up so they're no longer press fit. That way you can just pop the bearing on real quick, but that bearing won't be good for use. That would become your setup bearing. You'd use the bearing to set the pinion depth, and then you could tear it all back down and be like, yeah, I got the pinion depth purpose. I got the pinion depth perfect when I did this. So now I'll pull it back apart, pop these bearings off, because remember, they're not pressed. But then you'll actually put the brand new bearings on, and those will be pressed, and those will be one and done, because you've already done your setup bearing and goofed around with your shim, right? Because if you put your setup bearings in and your pattern is off, you may have to back it up and change this shim and then put it together again. Your pattern's still off, and back it up and change this shim again, right? And you need an assortment. That's what I'm saying. It's kind of a mess. And to go from installing this shim to this, you got to set the whole differential up just to get this pattern check. Okay. Now, when we go to do this pattern check, we actually have to put a pry bar on it and put some load on it and then spin it. And this would be a good pattern. Okay. This is an amazing pattern. If your preload and your backlash is in spec and your pattern looks like that, it's a beautiful thing. However, look at this. See the shading in here? It's too deep. That pinion is too deep. See, right? It's too low. Okay. That would be the toe side. Your heel is right here, your toe's down here. If you have too much toe side, let me back up to something, show you here. See this? The toe is down here. If your pinion's dropping down from this direction, which technically it's coming up from the other end, right? But it's easier to visualize if you picture it up here. The pinion always comes from the outside on the heel, and it always goes towards the toe. If it went too deep, can't you see how the shadow would be in here on the toe? Which would mean you need to decrease your pinion depth. It's too deep. It needs to be more shallow, right? It's too deep because this shim is too thick. So you need to remove some of the shim, put a thinner shim in, and then the pinion will go up higher, and then it won't be so deep in there. And that's really how you set the pinion depth. Cool, but the pinion depth is like the first thing you set, because you set this shim in there, but you set it by putting the shim in, but you can't really check it until you've done all the other steps. And then you basically are verifying it. Okay. Now, I'm going to say it like that because that's how it's taught through Toyota, through the region, through the factory training classes. But remember, I happen to come from another manufacturer. So if I could redo it, I probably would have went with Toyota, but that's not where I started. There's a benefit to that though. I've seen different ways of doing things. So it's sort of like maybe I'm a little more well-rounded. What I just told you is true per Toyota. But at the end, I'm gonna come back to this. I'm gonna say, check this tool out. This tool is how you set pinion depth for the domestics. And it's probably actually how they set it at the differential manufacturing plant. But in the field, everything I just said is how we do it. Okay. That's part of the reason that, guess what we're going to sell? A whole entire carrier. In the dealership, you're not going to really be building diffs. You might maybe do bearings, and you probably wouldn't, but you might. But full diff setup, not Toyota dealer work. Okay. All right. So if you look at this is how we're doing that pattern. And then if we evaluate these one more time, this one's too deep. This one is actually centered, but if you look, it's towards the root. So toward the root is a different issue, right? Heel and toe, that's pinion depth. Crown or root, that's actually backlash. So I don't sweat this a whole lot. This thing actually has too little backlash. This one's too, it's too into the root of the teeth. We just need to loosen the backlash up. I generally wouldn't use the gear compound for that because I can measure that with the dial indicator anyway, right? And then if you look at this one is to heel, which means the pinion is not deep enough. The pinion has to be deeper. That would be a thicker shim behind the pinion. And then this one is too much crown or top. That would be because your backlash is like this. It's barely touching. You need it to be like, you need to be in more. Make sense? So that's how this gear pattern will give you your explanation of how perfectly or non-perfectly aligned they are. So when we go to deal with that, we can do some fine tuning, which we'll come back with. Okay, when we cover the steps, I'm gonna talk you through it. Okay, but another thing is the preload. So if you look at this bearing is kind of pressing up against the outer race. To increase the tightness, we'd actually push down on it more. So when we go to adjust the preload, we're squeezing it more. If you don't have enough, remember it's sloppy loose and it messes it up. But if you have too much, it's too tight, it makes too much heat. There's no room for oil and it burns up. So you got to have your preload good as well. And typically we set the preload kind of while we're setting the backlash, but I would really set the preload kind of like first. Okay, so let's say we're going to set the preload for the pinion. When we go to set the preload for the pinion, we're tightening this nut. As we tighten this nut, it pushes this companion flange down, which squeezes these bearings together. It's going to pull the head of the pinion up. It's going to push the flange down. That's going to tighten those bearings up. It's really like this, tightening them up, tightening them up. So now you can see why when Richard over torqued that bolt, he over tightened those bearings. And as you do, it collapses this collapsible spacer or this crush sleeve. When it collapses it, it lets the bearings get a little closer, but you should be stopping and checking your preload and a little closer and checking your preload. If it's calling for, let's say, 7 to 10 inch-pounds of preload, and you go and you start, it's got 0, then it's got 1, then it's got 2. Tighten it a little bit more, check it. Tighten a little bit more, check it. What some people do is be like, I'm gonna tighten it a lot because I don't want to keep checking it, and they'll overshoot it and they'll be at 13, which you could probably get away with, but it's not really right. It's supposed to be 7 to 10, right? So to check it though, we put an inch-pound torque wrench on it and we spin it. Spin it around, and then it's like, okay, I'm getting a 4. Take that little inch-pound torque wrench that's this long, take it off, and then get the big breaker bar and hold the flange and tighten it a little bit, then take that off, and then put your inch-pound torque wrench on. Okay, we got 7, perfect, done. If the range is 7 to 10, don't be like, oh yeah, I really want to get 8.5. Like if it's 7, if it's 8, if it's 9, if it's 10, perfect, good, it's great. Don't be OCD with me. That's excellent. However, Richard took that nut and he sent it. And what it did was it overcrushed this crush washer, this crush sleeve, this collapsible spacer. Then remember, it didn't turn, so he loosened it. Now this collapsible spacer is overcrushed, and then it's just bouncing around in there. And these bearings, he loosened it up so it would turn, and these bearings were loose. You see what he did? How would you replace this collapsible spacer? Gut the diff, take the diff entirely apart, press the pinion out, and replace the bearings and replace the spacer. See, so that's why technically when you mess with that nut to take it off to replace that pinion seal, you're playing around with something a lot more serious than just the seal. You're playing around with that collapsible spacer. So that's what I'm saying. If you mark it and then you just tiny over tighten it, let's say you were at 7 inch-pounds. By the time you're done with the job, you're at 8 or 9. Great job. You can replace that pinion seal without going in and replacing this spacer. Per the service manual, a lot of manufacturers, though, they say you actually have to replace that collapsible spacer. It's one-time use. And I can't argue with it. I'm just saying, if you do it just right, you can get away with it, is what I'm saying. I'm going to operate on, being profitable, but also I'm going to save the customer money, and I can guarantee the work is going to be good, even though I'm not necessarily following what the book says. Okay. Cool. And then we talk about the side bearing preload. Remember, we were using these shims, we were pulling them and moving them, whatever. That's how you move the diff. That's how you move the ring gear. But also, the total number of shims is going to tighten your preload. So let's just say you happen to have your backlash perfect, but your preload was too loose. You could actually add shims to both sides equally, and that would tighten both your bearings. Makes sense? That's the visual. Now, in reality, that's why I was saying you're kind of adjusting preload and backlash at the same time. Because if you change, let's say that you put a bigger shim over here you've pushed the ring gear away from the pinion, which has increased your backlash, but it's also increased your preload. So you're kind of balanced. It's a balancing act. It's like caster and camber. If you change caster, you kind of change camber. And depending on if it's the A-arm style lower control arm or upper control arm, if you're adjusting camber, a lot of times you're changing caster too. So it's a balancing act, right? But generally, if you get your preload dialed in and you're happy with your preload, then it's almost like getting your caster set. Then you can fine tune your camber by turning both eccentrics together. It's like that. If you get your preload in spec and you're like, perfect, now I just got to fine tune backlash. Whatever you take out over here, add the exact amount over here, and that won't mess up your preload because the total's the same. If you have 100 and 100 thousandths shims, and this you got to drop down to a 90, you need to increase that to 110. The total has to remain 200 or whatever the number is that gave you your perfect preload. Okay, like that. All right, so now we're going to run through the steps. Okay, now that you're familiar with each of the steps, we're going to go through it. Okay. So let me think of how I would do this. If it were me, probably I would go with this. Set the side gear backlash. That's the small differential gears. We got to get all that stuff set first, of course. Then we want to actually make sure we don't have run out on our ring gear. Okay, because if we do, we got to deal with that. Then after that, we have to adjust our pinion preload. Okay, so if we go ahead and we put our little inch-pound torque wrench on there, right, we'd have to install the pinion. We'd have to put our little inch-pound torque wrench on there, and we'd have to turn it. And let's say it's 7 to 10, and we get it at 5. Then we take this back off, put the breaker bar on there, get the tool to hold the flange, tighten it some more. Okay, now we're at 8. Perfect, perfect, perfect. Okay. Then we have to install the center section, the ring gear, the case, if you will. And then what we're going to do is we're going to start kind of dealing with backlash, but at the same time, we're kind of doing pinion preload too. Okay, so as we're measuring the backlash, we can also go down here and spin this. But see right here, it's just the pinion because the ring gear is not installed. But once you have the ring gear installed and you turn this pinion, you're actually measuring both. Okay, so keep that in mind. Get your backlash dialed in. If you get your backlash in spec, which by the way, you might need to move, do shims and whatnot. But if you're spinning it and your backlash is wrong, remember, you just have to move the ring gear towards the pinion or move it away. Cool. But a lot of times what I'll be doing, I'll be looking at that total preload right there. If my preload is too loose, I'll just like put a bigger shim in. And then if my preload is good, but my backlash is still wrong, I'll measure both shims. And let's say that's where we got the 200 number, but my backlash is too loose. Let's say I need to move it towards it. Then I'll go with a smaller shim here by, let's say, 20 thousandths. And then I'll put a 20 thousandths larger shim here. And that way I got the preload. I didn't lose the preload. I'm just fine tuning the backlash. See what I'm saying? So if my total was 200, I do an 80 and I do a 120. And then I check my backlash. Once I get my backlash in spec, really, I'm pretty good. But the problem is I don't for sure know if my pinion depth is good. So that's why we do the painting. And then you load it up and spin it. And then you read the painting. And if the painting says your pinion depth is good, pretty much you're good. You're chilling. I would have put the collapsible spacer in right off the bat. I'd be like trying to hit a home run right here. I'd knock it out. But if I check it and my pinion depth is not right, because remember we went back here and let's say it was too close to the heel and I had to go deeper, that would mean I'd have to pull it all back apart. And then I'd have to change the shim on the pinion and then have to put it all back together. And then I'd redo 1, 2, 3, 4, 5, and 6. And then if 6 was good, then they say pull it all back apart, put your collapsible spacer in, put your pinion seal in, and then final torque it. right? They don't want you to use your seal and your spacer while you're just making sure it sets up. Okay, so that's kind of the process that, this is the Toyota process. The good news is that's not mainly the point of this presentation. We're going over the theory of it. When we do the actual work, we're going to go step by step by step, and you all will need to understand all the steps. Okay, but we can do that. Now, when it's talking about checking your side gear backlash, if your side gear backlash is wrong, there is no adjustment. All you can do is disassemble it and put a different shim behind it. There's not like a screw or a turn. There's, you got to actually take it apart and reshim it. Okay, that's normal. And you can see we're not on the ring gear, we're on the little side gear for the diff. Cool. Okay, and then here's the ring gear run out. This is going to be a lot of the steps, but more like zoomed in. Okay, here's the ring gear run out. We're actually spinning this and measuring the run out. The reason we do that now is like if the ring gear's got run out, you got to fix that. To fix that, you got to replace the ring gear. And actually, what you'd really do, you'd measure it and you'd be like, oh, the ring gear's got run out. You'd probably take the ring gear out and you might actually have to inspect the face of the case to see, is the case messed up or is it the actual ring gear? Make sense? Then after that, we're going to go ahead and we're going to start setting up the pinion preload. So let's say you started it and you snugged it up and then you put this on there and it was too low. You're just turning it lightly, right? This cannot in any way torque that nut. If you do, you're getting kicked out of class because it's already happened. People have busted the torque wrench right in half. Like this is not going to torque 140 foot-pounds. Look at the thing. Look at these hands. Them are soft hands. That's a soft hands right there. Okay, so we know. Spin it. If it's too low, take it back off, put the SST on there, and then crank it tighter just a little bit, and then check it, crank it tighter. Look, don't overshoot it. If you overshoot it, do not Richard it up and loosen it and have it fail. Okay, go and be like, hey, over tighten this. I think I need to take it all apart and put a new crush sleeve in there, a new collapsible spacer, if you will. Cool, but once your pinion preload is good, then you can go ahead and you can get your center section in, you get gear in, and that's when your balancing act between backlash, but you're also looking at spinning it again, your total preload. So if you had 7 to 10 before and you were at 8, and then it said the total should be 14 to 16, that would mean you had 8. You need to get an additional 8, 9, 10, 11, 12, 13, 14. You need an additional 6. So when you go to put this in, these bearings need their own preload. The problem is you can't read the preload for just these bearings because the way that you measure these bearings preload is you turn the pinion and the pinion has its own preload. So if you don't know the pinion preload, you can't determine the side bearing preload. Let's say you skip the pinion preload, right? You just skip it. Just like whatever. Put the ringer in, you turn it, you have 10 inch-pounds of preload. How much of that is the side gears and how much of that is the pinion? You don't know. You don't know. That's the thing. It's a formula. It's pinion plus side gear is total. So if you don't at least know pinion, you can't determine what side gear is, even if you can measure total. If all you know is total, it's A plus B equals 10. How much is A? How much is B? I don't know. But if A is 8 plus B is, let's say, 10, then you know B is 2. Right? So that's how you determine the side gear preload. You have to know the pinion first, and then you can measure the total, and by the calculation, you can know what the side is, okay? Kind of. Then while we're also doing that, we're also fine-tuning the backlash. So you want to be considering, like, if my backlash is loose, I want to add shims over here and I want to reduce shims over here, but my backlash is loose and my preload is too low, then I might just want to add shims over here. I might not take any out because that way it's going to shove the ring gear over, but it's also going to increase the tightness of the bearings. Make sense? So This is something I want you to spend a whole day on to really understand it inside and outside. Okay. And if you do, then you're chilling. And if you don't, then you got to work harder at it because you really need to know how to do this. The ASE is going to ask several questions on setting up a diff. I'll tell you right now. Cool. So this is when we were talking about the backlash. There's one thing I want to warn you about. If you have the ring gear hitting the pinion, it'll bind up and it'll give you like a false reading of high preload because the gears are really bound up. So just make sure at least while you're doing this, there's a little wiggle right there. Make sure there's a little backlash while you're trying to measure this. Here's your formula. Pinion plus side equals total. So if you had a pinion bearing of 13 and you got a total of 16, that would mean you have a side bearing of 3. Okay. You just can't measure the side bearings. That's kind of what I was saying. When you get all that all set up and your backlash is good and your pinion and your total preload is good because you measured the pinion and the total. So you know, the specs are 13. Actually, it didn't really show the spec, but let's say it was 13, and then the side bearing preload spec is 3 to 4. You know that you should be somewhere between 16 and 17. Let's say you did that, right? You got 13 and then you got 16 to 17. You're good. Last step, paint it, put a pry bar on it, spin it. Cool. If this is in spec, this one looks pretty good. It's maybe just a little bit toe side, but I'd be good with that. It's not real root. It's not real crown. That's good. Absolutely run that. Absolutely run that. Will you have problems? Nope. Would you have a problem if it was very toe or very heel? Yep. Would you have a problem if it was a lot of backlash? Yep. Would you have a problem if it was not enough preload? Yep. Would you have a problem if it was too much preload? Yep. Right. So if you don't have it where it needs to be, it's going to fail. Now you kind of see why a lot of shops won't do differential work. It's really not rocket science. It's just tedious, like you don't get to just slam brake pads and rotors on and ship it. You gotta take some time and set this up. But if you look at how simple it is, this is all you're working with. I mean, there's very few things there. It's not that hard. Then, of course, according to Toyota, because you didn't use the collapsible spacer and you didn't use the oil seal, you set it all up and you liked it. Then you're supposed to take it back apart and then put the new bearings on, put the new seal on, put the new collapsible spacer on, and then you just pretty much reassemble it with the shims that you selected and you should be good. Okay, that's what it's saying. Cool. And then make sure you have no flange run out because that'll send the drive shaft all crazy, give you vibration. Cool. So if you're gonna do like a additional overhaul process, it could really vary, but we're definitely going to change shims. We're definitely going to change bearings. We can reuse shims. The crush sleeve should be replaced. None of that stuff's usable. All right. And then this was just showing you a couple little bonuses, like that's that side gear preload. You could sometimes check it with a feeler gauge too. And this is that tool I was telling you about. You can't see it well, but this is a rig. It bolts up to the case. It goes over here. You're going to set it up the way service info says, and then it's actually going to have a dial indicator, and it's literally going to measure the depth of the pinion. And there will be a procedure, there will be a specification for that depth. So if this tool measures the depth and it's too shallow, you would reshim it right there. And if it's too deep, you'd reshim it. You could set your pinion depth using this pinion depth setup jig. Okay. Toyota doesn't list that. Toyota doesn't show any of that stuff. But so because where I came from, you can actually set this, but you have to have this special tool for this particular housing. It's not like a one size fits all. Like it's an SST for that differential housing. For let's say it's a Dana 44. You'd have this tool for Dana 44. You got Dana 44? I got the tool. Boom, boom, boom. I can measure pinion depth. Then you don't have to set it up and tear it down and set it up and tear it down. You measure this, you set it, you're good. You still have to set the pinion preload. You still have to get the ring gear and stuff in. You still have to set the total preload and the backlash. But then when you paint it, like it's more of a formality. You're not painting it to see if your pinion depth is right. You know your pinion depth is right. But again, I don't I'm not exactly sure why, but not in Toyota land. Cool. I've only seen, I've never done it. My mentor and foreman had done it, and I was like, "What the heck is that?" You know, so I knew about it, but I'm not a practiced hand at this. Full transparency. Cool. Driveline shops do that. Right. So then you check the thing, you check the actual measurement, and then you might have to do some math like, oh, the pinion depth is currently like 4.3, but it's supposed to be 53 thousandths less. So you might actually, you know, come up with whatever size shim you need or whatever it is. Cool. And then it would have a spec. So like this one is saying, if it was a GM 12 bolt, it's 4.670. Right. So this actually does have a spec, but I got to tell you, this may not be in service info. This looks like this is from like a specialist driveline, like maybe the manufacturer of that tool chart, right? Because no service information has Ford, Dana's, GM's, Chrysler. Like this is, and it's also old school because it says right there, American Motors, like a Rambler. It's old, but that stuff is out there. Cool. And then there's a shot of that shim. So if you did need to change the shim, that's why you take it out, measure it, determine how much thicker or thinner. There's quite a bit of stuff going on there. Okay. Now, when we're setting backlash, I think you'll mostly have understood we're dealing with these shims right here. So one thing I want to make sure you're clear on is even if you need to adjust backlash, those shims should be pressed in there because they need to give preload. Remember that? So the ASE had a question several times about you go up to this differential and you can't pull the diff out, you can't pull the center section and ring gear out, you got to pry it out. Tech A says somebody banged on it with a hammer. Tech B says it's welded. Like, no, that's normal. If you unbolt those caps and it falls out, that thing had zero preload for sure. So a lot of times when you get your shims figured out, you can set one in and kind of hold it. And then the other one, you usually have to use like a brass drift and you will have to drive it in with a hammer. And then when you go to take it out, you will have to pry the whole center section out with a pry bar. That's normal. That's totally normal. Make sense? The ones you guys are gonna be doing at school actually have threaded adjusters. They're amazing. You don't need shims. You can set the preload and the backlash all with threaded adjusters, but they're a little more expensive to make. So most vehicles don't have them because most vehicles never get the diffs done. Like, why give an adjuster that's never touched? Type of thing. Cool. Now we talked about diffs. We already talked about open diffs and LSDs, but now we're going to go through the LSD types. This one, for example, just as the example, this one is an electronic locking differential. And this one is a clutch pack type LSD. All right. So in a way, they're a little different. This is a locking diff and this is a limited slip diff, but it never really locks. Okay. But we're still going to put them both under LSDs. All right. So if it's a clutch type, if you look right here, you've got steels that are lugged to the case, which is spinning, and you've got frictions, clutches, which are splined to the axle. And so if we activate that clutch pack, it locks the axle to the case and it forces the axle to turn. Now, how do we lock it? Well, that kind of depends. Let's take a look at this. This has a preload spring, and this is basically trying to push this side gear up against its clutch plates, right? So the clutch plates live in here. Your side gear, which is in like light red, is trying to push up against those clutch plates. The harder this side gear pushes up against those clutch plates, the more it locks the axle to the housing, right? Because of the steel is on the case and the friction is on the axle. The more we squeeze that, the more that clutch pack is squeezed, the more it's going to turn it. How does it get squeezed? This spring is going to give it a bit of preload, but then what's really going to happen? If you were to do the one wheel peel and this was turning really fast and this one was turning 0 miles an hour, can't you see how these gears are going to spin, right? And when these gears spin, if you have gears like this, if this top gear is spinning it tries to throw this gear out, right? The faster you turn this gear, it tries to throw this gear more. Well, the faster you have both of these gears turning, it tries to throw these gears like this, right? So if you're going straight and you're turning a little bit, it's like, you know, you might get a little bit of turn and the gear's like no big deal. But if you get in a one wheel peel, those are going to spin so fast. These gears are going to get thrown really hard. That's going to squeeze the clutch pack. That's going to squeeze the clutches together. So it's purely mechanical. It's a pretty good design, actually. The negative, though, they do have clutches, and those clutches do wear, and those clutches do require a special type of lubricant that has a clutch additive. So if you put regular oil in a if you put regular gear lube in an LSD with clutches style, those clutches are going to stick and bind. And there was even some TSBs on it where you'd go around a turn and the clutches would kind of stick. Do you guys recall I told you about how I ruined a power steering pump? Well, I'm going to retell it. I ruined a power steering pump. It was on a really ugly car, the Pontiac Aztec. I almost called it what we called it in the shop. We called it the Az Crack, but it was an Aztec. Okay, it was just ugly. It was kind of cool. The center console was a cooler. It didn't cool, but like if you flip the handle one way, you could pick up the whole center console and carry it with you, and you could put your lunch and stuff. So like it had some cool ideas. They just made it too ugly. On the Aztec, they had an issue with the clutch pack. It wasn't exactly a differential. It was actually an all-wheel drive, and it had the viscous clutch, but they had clutch discs. And a lot of times the incorrect lubricant was used, or it would have debris or whatever. But when you'd go around turns, the clutches would try to grab and it would shudder. Okay. So the fix was drain that fluid, the correct fluid in, and then go drive it in 30 left-hand loops, 30 right-hand loops, and then 30 figure eights. And so I tried to do it really fast, and I went out to the parking lot and locked the wheel all the way one way. When you're turning, those clutches slip, right? So when you're turning, it's thinking the new fluid's coming in, it's going to slip the clutches and get the old fluid rinsed out of it. So I did 30 lefts, 30 rights, 30 figure eights, came in, drained the fluid. Fluid was nasty, put the new fluid in and drove it, and all the shuddering was gone. The reason it was shuddering was the clutch discs were sticking because the wrong oil was used, or maybe because there was some clutch material and gunky debris, right? So they would stick and slip and shudder. Okay. So if you use the wrong oil, those clutches are going to tend to slip. That's why they have a friction modifier. They're going to try to stick, slip, they'll cause some shudder. If they stick and then slip, they're wearing out. So they're wearing prematurely. Okay. So that's why we have the additive. You can put the additive in an open diff. You're just wasting money. So shops back in the day would have limited slip oil and regular oil, but then so many people would screw it up. They were like, you know what? We're just going to have limited slip oil only. It's a little more money, but at least we won't possibly have messed a car up. Makes sense. So that's like giving you some backstory. Now, how I burned the power steering pump up was I held it all the way to the power steering lock for 30 lefts, all the way for 30 rights. And between holding it for like 10 minutes, I killed the pump. When you turn the steering wheel all the way to the lock, it works the pump at 100% effort, and it killed it. Okay. But the reason I did was because of these clutches, just like that. All right, cool. Now continuing, if you were going to try to measure whether those clutches are good or bad, there's a lot of people who tell you a lot of things. The best way to do it, okay, not the best at all. The most thorough way to do it is to get it out there and do a burnout and see if both wheels spin and mark up that blacktop. If you get a ticket, that's on you. I'm not telling you to do it that way. So don't you pull this video out and show the policeman. Hey, officer, my teacher said, no. I'm saying that is the most effective way. But it comes with a ticket, so we're not going to do that. So what we're going to do, leave one wheel on the ground, go to this other wheel, and you're going to actually measure how much torque it takes. If it's a good clutch pack, it shouldn't be easy to turn this, right? So if you start to try to spin it, those clutches are going to really pump up. Now, the negative is this is kind of old school. This is a true Positrack. This is old Positrack. Does that car have a Posi? That's hot rod stuff. So these actually had quite a bit of friction. They had a lot of preload on these. So you could check it like that. On a modern car, that's not going to work. On a modern car, the best thing you could do is probably get it up on the lift and get it up to speed and see if it engages both wheels, but that's not really testing it under load, so it's actually pretty tough. But I had a guy, we did an inspection on a 69 Camaro and his broker's like, yeah, let me check the posi track. And I see him over there spinning the wheels. I was like, what are you trying to do? He's like, well, this is how we check them. So on the old posi tracks, literally, if you turn the diff, if you turn the drive shaft, both wheels would turn. And if you kind of try to drag one, it would pull it out of your hand. On the new one, they don't put that much tension on those clutches. You got to like really get it up to speed for that to work. Makes sense. But on the old ones, like the True Posi on that 69 Camaro, that one was pretty tight. I was surprised. That was the first time I ever saw that. Right. So if it was on a new car and you really wanted to check it and you were kind of feeling dangerous, yeah, you could get up to speed, get them both spinning and try to grab one. And if you can stop it, it ain't working. And if you try to grab one and you feel like it rips it out of your hands, oh yeah, it's working. But if you hurt yourself, you're fired. I didn't tell you to do that. I'm not telling you you should. I'm telling you someone else could. Primitive Pete would do it. Tech B would probably do it. All right, types of diffs. This is a Salisbury. This is a little bit more of a race type one. This one right here does have clutches. The way we engage those clutches isn't just due to the spider gear spinning and centrifugal force. It's actually like it kind of is, but it also has to do with this pin. So when you try to drive this pin, you'll notice it can ramp. So if you start to slip, this pin is going to move and it's going to start to ramp up on these and squeeze the clutches. It's really hard to see while it's stopped. But the good news is there's another discussion you're going to do, which is on LSD types, limited slip differentials, that is. So you're going to learn in animation all these different LSD types. So they have these as like a 50-75. It's more biased towards locking up and forward and less in decel, right? So if you're excelling, it's going to be 75% and decel would be 50. And so if you're on power, the power ramp is a little more exaggerated and the coast ramp's a little smaller. So you're getting more lockup on power. 45-45 would be like a split. If you have a 45-90, that's going to be like almost all XL and just a little bit of lockup on decel. You know, they have all these different splits. So it all has to do with the shape of the ramps and the pin. All right. So when you go to accelerate, this ramp is going to squeeze, is going to expand and lock those up. But when you go to decelerate, it's not going to generate a whole lot of force right there. This one's going to do the same. When you accelerate, it's going to give a lot of spreading force. When you decel, it's going to give a lot of spreading force. It's a 45-45. It's the same. Sometimes they'll call them way. It's like one way, 1.5 way, you know, depending on the exact terminology. Right, but this is a little more like race car stuff. You can see this one's basically going to do really very little to no locking on decel. You can see it's all ramped on the acceleration and it's generating no expansion on the decel. So that's the Salisbury type. The G80 was what we were talking about on that van. This one, again, the animation's amazing, but the flyweight will actually engage an arm, which will ramp this plate up, which will squeeze those clutches. So these have clutches too, right here. These have clutches. Cool. So this would all be stuff that could wear out. This is like that Eaton. So this is the flyweight. So there's this special types of mechanism and a little spring and stuff like that. Okay, and this is the wave plate and the fuse plate, and they will actually have the clutch discs as well. And the cone, those can tend to vary. So they'll call these, they can come in different types. Most of them will have clutch packs. There are some other types that use more like almost like a synchronizer ring, like a blocker ring too. But now we're into something different. Torsen is very unique. So again, you got to do this discussion for these animations, but just as the lesson, the Torsen has no clutches. This is a complete gear to gear limited slip. So it's hard to explain, but it has to do with the types of gears. So you'll watch that, and it's going to use a worm gear, and the worm gear is interesting. It can be turned, but it can't turn. So if you're going around a turn, it'll freewheel, but like if you accelerate, it'll lock up. It's very interesting. But look, no clutches. So if there's no clutches, we don't need to worry about the clutches wearing out. The Torson's amazing, and it's pretty ingenious, really. So if you go with a Torsen, you're not worried about clutches. All these other one clutches, 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 and that's not bad. But the Torsen's pretty stinking nice, not gonna lie. The only thing I like better is a full e-locker. But this wouldn't be for a car. If it were for a car, I'd probably prefer the Torsen mostly. But if it was for off-roading, I'd rather go with the e-locker, because if you lock the e-locker, it's engaged, right? So this actually has a solenoid or sometimes a motor, and it will literally motor over a fork and lock the sleeve. So it's pretty neat. Cool. So that's it. And we come back to that one more time too. But you need electrical connections here, which means you need a computer to control it, and you need a diff lock switch. So even on the two-wheel drive, like the pre-runners, you'd get a two-wheel drive pre-runner, but it would say diff lock. That's actually pretty cool. If you lock the diff in a rear-wheel drive, you can go places. Maybe not quite as good as a four-wheel drive, but definitely getting closer. Cool. But as a reminder, the limited slip clutches, whether they're one type or another type or another type, these have clutches and steels, and those clutches wear like in an automatic. And that's why we need the special oil. And that's also why, they tend to not be my favorite. Like eventually those are going to wear out, especially if you're driving hard. And that's why it calls for this differential gear oil with specific limited slip additive, right? Special additive. I don't know if this one has it. Actually, I don't remember. But this one just kind of shows that motion. As you get a big speed difference, these spiders turn faster, and this gear turns fast, and that throws this gear up against those clutches. And that'll give you your LSD work. And then there's a whole bunch of different type of full-on lockers, right? No clutch. These ones actually just engage. They're using dog clutches. So if you get spinning fast enough, I got to get the mouse over here in the right spot. This axle will be splined to this plate, and it'll actually engage right here and lock on that like a manual, like a dog clutch, almost like the dog teeth. Click, it'll be a full-on lock. But other types, they do have more like a soft locker that'll not really exactly lock, but like kind of grab, but they make a lot of different stuff. And then we get into something you have to understand is viscous clutch. So this is an example of a viscous clutch. The viscous clutch has clutch packs. We wouldn't generally use this in a rear diff. We generally use this in a transfer case on an all-wheel drive. Because remember, all-wheel drive is all-wheel drive all the time. And that's all it will ever be. You don't push a button in an all-wheel drive, generally. So if we want it to activate itself, one of the things that we could do, we could actually use, it's like a viscous fluid. It's like a type of silicone. When it's interesting, but when it is cold, it will be kind of loose. I think this is actually backwards, but when it's cold, it's pretty easy to move. When it's loose, it gets thick. All right, so that's what this was trying to show. This is actually like building up more. So if you had a viscous coupling and you were just going down the road, the viscous coupling is pretty soft, it's pretty easy. But if you start slipping in the snow, that slipping will heat it up. And when you heat it up, it'll actually kind of solidify, and that will cause these clutches to engage. And when these clutches, they don't just engage or disengage, they'll progressively engage. The hotter it gets, the more they engage. And so that's how it will automatically stop the differential action. So if you have an all-wheel drive, it's trying to drive front and rear, but there's these clutches and they're loose. So if you were to spin the front tires, the rear would not do anything. But as you spin the front tires and you don't spin the rear, that movement on those clutches is going to actually heat up this viscous fluid, and that viscous fluid is going to pump up the clutch pack and make the rear drive shaft turn more. And then you have like it from the wheels that slip to the wheels that grip. There you go. From the wheels that slip to the wheels that grip. Front wheels were slipping, heat up the viscous fluid. Rear wheels are now gripping. Okay, we can do it better now though than viscous fluid, but we could do it purely mechanically with viscous fluid. What we'll probably do now is an actual clutch pack, and we'll control that with a motor or a solenoid. We could even use pressurized fluid, like if it's a Subaru and the Subaru's got pressurized fluid through an oil pump, we can pump that clutch pack up with ATF or similar. Okay, so regardless, the way that the all-wheel drive works, it's not exactly a differential because there's no spider gear type of stuff always happening, but there's clutches, and the clutches allow it to slip, so that allows a speed differential. But then when there's too much slip, it pumps the clutches up, so that stops the speed differential. And that's why it's a differential, but barely. Cool, so that's kind of an interesting one. And then we got some computerized stuff. Auto LSD is basically an open diff. You have an open diff right here, but if you see the wheel slipping, that left rear wheel is slipping because you're in the snow, because you got too close to the, whatever, the median. When that wheel slips, the ABS sees that through the wheel speed sensor, right? And it says, hey, left rear wheel slipping. Oh, I know what to do. Apply the brakes, right? The skid control ECU can apply the hydraulic brake booster, not a vacuum booster though, but the all electronic big hydraulic brake booster. It'll run the motor, or it'll use the brake fluid that's stored in the accumulator, send it through the valve in the ABS, and grab that left rear caliper. Remember, the torque takes the path of least resistance. What's the path of least resistance now that the brakes are applied on the left rear? Send the torque over to the right, which has traction, and there you go. You're rolling. You're off and rolling now. Cool. So that's the auto LSD, which is a great feature, by the way, without having to really add limited slip differential components. Okay, and then there's another type of differential that's called the ADD. We're coming up to this next week as well. Automatic disconnecting differential. So when you're in two-wheel drive, this motor pulls this fork out, and basically it disconnects this axle, which makes it so when you're going down the road, the wheels don't turn the diff, which don't turn the drive shaft. If all that was splined up, it would turn the drive shaft. But when we pull the ADD, the wheel turns the axle, and this shaft just freewheels, which means this axle just freewheels. It doesn't turn the actual diff. Now, when you put it in four-wheel drive, if the ADD were to not work, the four-wheel drive will turn the drive shaft, but the drive shaft will just spin the center section, and all the torque will go to this disconnected axle, and the car won't get four-wheel drive. We need to engage the transfer case next week, but we also need to activate the ADD, which will engage this fork, which will then make this actually function as a differential. Cool. Why is this here? This is four-wheel drive work. I'm going to tell you, because I got a call a couple years ago from a student who came through, and he was under the impression that the ADD makes this a locking differential. And I realized I need to do a better job explaining this. This is not a locker. This is an open diff. It's an open diff that we basically disconnect a side gear on so that it doesn't back turn the transfer case all the time. If you're going down the road in two-wheel drive, we don't want that drive shaft turning. We don't want it wasting gas. We don't want any of this stuff turning. So we disconnect it so it's just sitting there. When you connect it, all it does is it makes it function like a normal open diff. That's it. So there you are, two-wheel drive, and you're like, oh no, I'm going off-road. Bang, four-wheel drive, shifts the transfer case. We'll cover that. And then this diff moves this motor, boom, and it just makes it a diff. It makes the diff function. Without this ADD connected, it's almost like a regular differential with a broken CV shaft. That won't move. The torque will go to the broken part and just spin this part. Cool. So the ADD, only on four-wheel drive, it's a type of differential, but not a locker, right? And then it's got this motor and detection switches. So this is how it knows if it's engaged or not. When you push the four-wheel drive button, yeah, it tries to shift the transfer case, and that's got its own stuff happening, but it also monitors your front differential. And if your front differential doesn't close, like right here, it's got a position switch. If that doesn't close, it knows that front diff didn't engage. Your four-wheel drive light will continue to flash. That way the customer knows, hey, my four-wheel drive didn't go in, or my four-wheel drive indicator never lit up. Like it's just they know it might fail. It's just a way to verify, hey, the four-wheel drive is working or it's not working. Okay. And this is what happens. You go from on the switch, you go from 2 to 4. It shifts the transfer case. That is seen, which then tells the ADD to engage. And then if the ADD is seen, then the highlight for four-wheel drive highlight comes on. Then you know it's in four-wheel drive. You're chilling. Okay. It's the main thing. Now, that's all about the theory of diffs. If you were to rebuild a diff, you're going to pull the clutch packs out, inspect them for wear, inspect the steels. You can see the steels are splined in this case actually to the side gear, and the frictions are actually splined in this case to the housing, to the case. It doesn't matter. Whatever. Same thing. If it engages that clutch, the axle is now locked to the spinning center section. And that's why it will burn the tires, both sides. Okay, so inspecting for leaks. If you're going to do these clutches, you have to soak them for 15 minutes with the correct friction modifier. You got to know that. You don't put dry clutches in there. You got to have it soaked, and it needs to have the friction modifier. Doesn't that look delicious? It's like honey. It'll be like amber pretty soon. Okay, and then we're going to set it up, build the clutch pack. A lot of times that you have to do like some sort of a compressor or a spring, and then we can measure the end play, the clearance. So you can see this is a little bit more involved than an open diff, isn't it? And then that one would be ready to go. Put them in, put it in the side case, reassemble the diff like normal. And then the purpose of this S spring is very simple. It puts a little bit of tension on the clutches. If you didn't have that spring there, it would have no preload. I'm not sure the clutch pack would ever really engage. You'd lose your limited slip. Makes sense? So this is just a preload spring. You gotta pop that one in, put the clutch in. Now for concerns, okay? Because we're getting down there. For concerns, generally, we're worried about the source of that. So we want to consider the customer's write-up. We want to do a good road test, and we may use something like the chassis ear or similar to really narrow this down. So is it a noise? Is it a vibration? What is it? Customers can have a hard time explaining that. They're sort of like, well, I feel, I hear a vibration. You don't hear vibrations. Do you understand? Hearing means it's a sound. Feeling is a vibration. So if you hear it, it's a sound. If you feel it's a vibration. With that being said, any sound is a vibration. Right? Your eardrum picks up vibrations in the air. So they are related, but we just want to be able to get the customer to explain clearly. If they say, I hear a vibration, you say, no. Hearing is your ears. Feeling is like, what do you feel? And try to help them narrow it down. When is it noticeable? When did you hear it? When did it start? What's the history? Has it ever been done this before? Have you had any recent work? What are you doing? These are important things. What's up? Are you giving it gas? Is it acceleration, deceleration, light throttle, medium throttle, heavy throttle? What are you doing? What type of road conditions? Is it while turning, right? Because remember, we talked about all those gears. If it was that pitted, worn out differential gear, that would happen on turns. So a lot of times, some of the questions are going to help. And then additionally, your road test is really going to narrow it down, right? So do all these different drives, make note of when it occurs, but be warned. Exhausts make noise. Tires make noise. Like, don't just jump to the differential, especially tires. So we had one that would make a lot of noise. If you have a bunch of noise and then you put it on the lift and the noise is gone, it's not a real good way to test the diff, but it's a real good way to test the tires. If you have it on the lift and it's still making the noise, it's definitely not the tires. Make sense? However, when you're on the lift, you're not putting a lot of load on the diff. It might not make the noise as much in the air. See, so that's why we jumped into maybe having the chassis ear. Okay, so some example noises. If you were to have a chuckle, you know, that could be almost like it sounds like you put your cards in the spokes and it makes a sound. If it's varying with speed, it could actually be gear tooth damage. Knocking, well, let's say that's similar to a chuckle but much louder. That could be gear tooth damage. But let me add to this. What if it was chuckle or knocking only during turns? That's when we'd start to look at those spider gears. Or what if it was happening only on, let's say, well, I don't know if it would only happen, but it's more noticeable on XL or on decel, right? Then that would be more like, okay, I'm into the ring and pinion specifically. Or if it's chattering, I told you that about the Aztec. If it chatters, that could be a number of things, but if it's chattering while turning, that's when those LSD clutches have to slip. And if they're slipping and sticking and slipping and sticking, that would absolutely cause a chatter. And that might be, as you see, maybe worn clutches or incorrect lubricant. Now, bearing noises. I'm going to lump both of these bearings together. But first, we're going to do gear noise. So when we talk about gears, if you have ring gear and pinion gear whine or ring and pinion gear issues, they'll kind of sing. You'll be going down the road, especially that van that was a hollow big echo chamber. You could hear the diff in those. Brand new. It'd be just and but in the van with the full interior with actually seats and stuff in it, you wouldn't hear it. So first off, you got to determine, is it normal, abnormal? There can be some noise normally from the factory. But if it is abnormal because you compared to another known good same vehicle, fine. If it changes with acceleration or with deceleration, you got a pretty good idea that that's ring and pinion wear, right? You'd inspect them and you'd look. That would be a gear type of noise. Same thing with the turning. If it's only while turning, that's all gear type of noises. Those sound different than bearing noise. If it's really singing, if it sounds like it's singing, that's gear stuff, especially if it's high speed. If it's more like a growl, that's bearing noise. Then you have to figure out, is it high pitched or low pitched? Remember, so if you've got a pinion bearing noise, that pinion is turning 4 times faster than the side bearings and the axle bearings. So if it's kind of like woo, but you can change it. Remember, woo, then I'd be thinking like, maybe pinion bearings. But if this pitch doesn't change it, but turning the wheels do, maybe you'd be thinking those axle bearings, but those are generally a deeper pitch, right? Because they're turning a lot slower. Then, of course, the chassis ear is going to help you a lot too. Okay, kind of decent on the noises, hopefully. Kind of decent on overall differential stuff, because pretty much that's where we need to be. Then, of course, if the fluid was low, you could always say, hey, you know what? When the fluid goes low, it ruins that front pinion bearing. That's the one that's the furthest up. So the fluid gets starved for that one first. You can do some of these different factors and consider some of that type of stuff as well. Okay. Now is your chance. You got any questions that you think will help the presentation? Ask them now. Let me look up something hit in the chat. It is, there's a lot of stuff. Diffs is a lot. But keep processing it. And you could rewatch that video and you could do the LSD ones and stuff, but when it gets to servicing it, don't even worry. You got plenty of time to understand the service by doing the service. But the theory, though, you should try to get that pretty dialed in by next week. Continuing. Any more questions or comments about my brain hurting?
Just had a quick question. How long do you think it's gonna take to like fully understand differentials?
Probably a lifetime. No, to be honest, when I came out of school, I didn't really understand diffs. I thought I did, and then it was like when it was time for me to teach the class, I realized like I can picture it in my mind, but I don't understand it well enough to explain it. So to be really honest, if you want to really get it, keep thinking about it, talk about it. Talk about it with the other people who are in class and be like, well, I think it does this and I think it does that. And if you come to me with your questions, I can straighten you out. But it took me a lot of effort to understand it. So once in a while you'll overhear me. Sometimes I'm talking with people at the school because like Clyde teaches some hard classes. Um, Mr. A teaches some hard classes, kind of, but you know, when Beard retired, he was the full-time transmission guy. People underestimated him. And so now we're looking to replace him. And they're like, oh, well, I know somebody who teaches over here. And it's like, but what do they teach? Well, like engine performance. I'm like, dude, like this, the transmission class, there's a lot of stuff. That's what you'll hear me say. Like that class is a beast. I always find myself saying that. That class is a beast. Don't underestimate it. They put a couple subs in there this semester, and the one sub was like, I really can't do this. And the other one, you see, they're still covering manual transmissions. They're literally in there doing. They have done nothing on automatic. So this class is a beast. There's just so much stuff, and to really understand it, it's you got to work a lot at it, but it covers a lot of different areas of the car, you know. So like electrical's amazing. You need to know electrical thoroughly, but you're really only learning electrical. You're not learning, you know, differentials and manual transmission transaxle and automatic transmission transaxle, CV axles and drive shafts and four-wheel drive and torque converters. You know, like this class is a beast. But it's a lot of the, you know, it's a big, there's a lot of these components on the car. So if you can really grasp this, it is going to help you, but don't feel like if you're not understanding it, you're dumb. It was really hard. It took a lot of dedication for me. Videos, talking, listening, watching, on top of after I graduated and I already passed the ASE. So I had to have my ASE for 12 years before I taught this class. And then I was like, man, I thought I knew, but like to really know, you got to really work at it. So it's going to be a work in progress, Roberto. Don't beat yourself up. Points. You guys got anything else? I'm gonna end this recording so it'll start processing because this one you can tell like this is to add